JavaFX architecture. Here you can see a architectural diagram of JavaFX. JavaFX is a software platform for creating and delivering desktop applications as well as rich web applications that can run across a wide variety of devices. JavaFX has support for desktop computers and web browsers on Microsoft Windows, Linux, and Mac OS, as well as mobile devices running iOS and Android. Here you can see the system architecture. The JavaFX architecture diagram shows the stack. The top layer shown in a rounded maroon box represents the JavaFX public APIs and the JavaFX scene graph. Next layer is a quantum toolkit, a rounded blue box. The third layer has the graphics pipeline called Prism in a rounded blue box, glass window in toolkit, glass in a square pea green box, media engine in a square bright green box, and a web engine in a square brown box. The fourth layer consists of Java 2D, OpenGL and Direct 3D, D3D in a rounded blue boxes, quantum toolkit, Prism, Java 2D, OpenGL and D3D, all shown in a rounded blue boxes, make up the JavaFX graphic system. The lowest layer shown in a light purple is a Java virtual machine. The Java virtual machine sits underneath the JavaFX graphic system. Glass window in toolkit, media engine and web engine. The JavaFX is a set of Java libraries designed to enable developers to create and deploy rich client applications that behaves consistently across platforms. Figure 1 illustrates the architectural component of JavaFX platform. The sections shown in the diagram describe each component and how the parts interconnect. Below the JavaFX public APIs lies the engine that runs your JavaFX code. It's composed of subcomponents that include a new JavaFX high-performance graphics engine, called Prism, a new small and efficient windowing toolkit called Glass, media engine and web engine. Although these components are not exposed publicly, their descriptions can help you to better understand what runs a JavaFX application. Scene graph. JavaFX scene graph, shown as a part of the top layer in this figure, is the starting point for constructing a Java application. It is a hierarchical tree of nodes that represent all of the visual elements of the application's user interface. It can handle input and can be rendered. A single element of a scene graph is called a node. Each node has an ID, style class, and bounding volume. With the exception of the root node of a scene graph, each node in a scene graph has a single parent and 0 or more children. It can also have following effects such as blurs and shadows, opacity, transforms, event handlers such as mouse, key and input method, and application specific state. Unlike in swing and abstract windowing toolkit (AWT), the JavaFX scene graph also includes the graphic primitives such as rectangles and text, in addition to controls, layout, containers, images, and media. For most users, the scene graph simplifies working with UIs, especially when rich UIs are used. Animating various graphics in the scene graph can be accomplished quickly using JavaFX animation, JavaFX.animation APIs, and declarative methods such as XML doc also work well. The JavaFX.scene API allows the creation and specification of several types of content such as nodes, shapes, 2D and 3D, images, media, embedded web browser, text, UI controls, charts, groups, and containers. Next point, state, transform positions and orientation of nodes, visual effects, and other visual state of content. Next point, effects, simple object that change the appearance of a scene graph. Nodes such as blurs, shadows, and color adjustment. The public APIs for JavaFX features. The top layer of the JavaFX architecture shown in this figure provides a component set of public APIs that support rich client application development. These APIs provide unparalleled freedom and flexibility to construct rich client applications. The JavaFX platform combines the best capabilities of the Java platform with comprehensive immersive media functionality into an intuitive and comprehensive one-stop development environment. The new Java APIs for JavaFX features. First point, allow the use of powerful features such as generics, annotations, and multi-threading. Make it easier for web developers to use JavaFX from other JVM-based dynamic languages such as Groovy and JavaScript. Allow Java developers to use other system languages such as Groovy for writing large or complex JavaFX applications. Allow the use of binding, which includes support for the high performance lazy binding, binding expressions, bound sequence expressions, and partial bind re-evaluation. Alternative language like Groovy can use this binding library to introduce binding with syntax similar to that of JavaFX script. Extend the Java collections library to include observable list and maps, which allow applications to via user interfaces to data models, observe changes in those data models, and update corresponding UI control accordingly. The JavaFX APIs and programming model are a continuation of JavaFX 1.x product line. Most of the JavaFX APIs have been ported directly to Java. Some APIs such as layout and media, along with many other details, have been improved and simplified based on the feedback received from the users of the JavaFX 1.x release. JavaFX relies more on web standards such as CSS for styling controls and area for accessibility specification. The use of additional web standards is also under review. Graphic system. The JavaFX graphic system shown in blue in this figure is an implementation details beneath the JavaFX scene graph layer. It supports both 2D and 3D scene graphs. It provides software rendering when graphics hardware on the system is insufficient to support hardware accelerated rendering. Two graphics accelerated pipelines are implemented on the JavaFX platform. Prism. Prism processes render jobs. It can run on both hardware and software renders, including 3D. It is responsible for rasterization and rendering of JavaFX scenes. The following multiple render paths are possible based on the device being used. DirectX 9 on Windows XP and Windows Vista, DirectX 11 on Windows 7, OpenGL on Mac, Linux embedded, Java 2D, Java 2D when hardware acceleration is not possible. The fully hardware accelerated path is used when possible, but when it is not available, the Java 2D render path is used, because the Java 2D render path is already the Java 2D render path is used because the Java 2D render path is already distributed in all Java 2D runtime environment JREs. This is particularly important when rendering 3D scenes. However, performance is better when hardware render paths are used. Quantum Toolkit tied Prism. Quantum Toolkit ties Prism and Glass Window in Toolkit together and makes them available to JavaFX layer above them in the stack. It also manages the threading rules related to rendering versus event handling. Glass window in Toolkit. Glass window in Toolkit shown in beige in the middle portion of this figure is the lowest level in the JavaFX graphics stack. This means its main responsibility is to provide native operating services such as managing the windows, timers and surfaces. It serves as the platform dependent layer that connects the JavaFX platform to the native operating system. The Glass Toolkit also responsible for managing the event queue. Unlike the abstract window in Toolkit, AWT, which manages its own event queue, the Glass Toolkit uses the native operating system event queue functionality to schedule thread usage. Also, unlike AWT, the Glass Toolkit runs on the same thread as the JavaFX application. In AWT, the native half of the AWT runs on the thread and the Java level runs on another thread. This introduces a lot of issues, many of in which are resolved in JavaFX by using a single JavaFX application thread approach. Threads. The system runs 2 or more of the following threads at any given time. JavaFX application thread. This is the primary thread used by JavaFX application developers. Any live scene, which is a scene that is part of the window, must be accessed from this thread. A scene graph can be created and manipulated in a background thread, but when its root node is attached to any live object in the scene, that scene graph must be accessed from the JavaFX application thread. This enables developers to create complex scene graphs on a background thread while keeping the animations on live scenes smooth and fast. The JavaFX application thread is a different thread from the Swing and AWT event dispatch thread, EDT, so care must be taken when embedding JavaFX code into Swing applications. Prism render thread. This thread addresses the rendering separately from the event dispatcher. It allows frame n to be rendered while n+1 is being processed. This ability to perform concurrent processing is a big advantage, especially on modern systems that have multiple processors. Prism render thread may also have multiple rasterization threads that help offload work that needs to be done in rendering. Media thread, this thread runs on the background and synchronizes latest frames through the scene graph by using JavaFX application thread. Pulse. The pulse is an event that indicates to the JavaFX scene graph that it is time to synchronize the state of the element on the scene graph with Prism. The pulse is throttled at 60 frames per second FPS maximum, and is fired whenever animations are running on the scene graph. Even when animation is not running, a pulse is scheduled when something in the scene graph is changed. For example, if position of a button is changed, the pulse is scheduled. When a pulse is fired, the state of the element on the scene graph is synchronized down to the rendering layer. A pulse enables application developers a way to handle events asynchronously. It is important this important feature allows system to batch and execute event on the pulse. Layout and CSS are also tied to pulse event. Numerous changes in the scene graph could lead to multiple layout or CSS updates, which could seriously degrade performance. The system automatically performs the CSS and layout pass once per pulse to avoid performance degradation. Application developers can also manually trigger layout passes as needed to take measurement prior to the pulse. Glass window in Toolkit is responsible for executing the pulse event. It uses high resolution native timers to make the execution. Media and images. The JavaFX media functionality is available through javafx.scene.media API. JavaFX supports both visual and audio media. Support is provided for MP3, AIFF, and WAV audio files and FLV video files. JavaFX media functionality is provided as 3 separate components. The media object represents a media file. The media player plays a media file, and the media view is a node that displays the media. The media engine component shown in this figure has been designed with performance and stability in mind and provide consistent behavior across platforms. Web component. The web component is a new JavaFX UI component based on WebKit that provides a web viewer and full browsing functionality through its API. This web engine component shown in orange in this figure is based on WebKit, which is an open source web browser engine that supports HTML5, CSS, JavaScript, DOM, and SVG. It enables developers to implement the following features in their Java applications: render HTML content from local or remote URL, support history and provide backend forward navigation, reload the content, apply effect to the web component, edit the HTML component, execute JavaScript commands, handle events. This embedded browser component is composed of the following classes. Web engine provides the basic web page browsing capability. WebView encapsulates the web engine object, incorporates HTML content into an application scene, and provides fields and methods to apply effects and transformations. It is an extension of a node class. In addition, Java calls can be controlled through the JavaScript and vice versa to allow developers to make the best of both environments. Here you can see in top JavaFX public APIs and scene graph. Below you can see Quantum Toolkit, and below that you can see Prism, and below Prism Java 2D, OpenGL, and D3D, and below Java Quantum Toolkit you can see a glass window in Toolkit, web engine, and media engine. Below those you can see API, JDK API and libraries, and JDK API libraries and tools. Below that you can see Java virtual machine. You can see JDK API libraries and tools are in this area, this line also. Here you can see architecture of JavaFX in a different view. JavaFX has numerous built-in elements that are interconnected with each other. JavaFX library comprises a valuable collection of APIs, classes, and interfaces that are more than sufficient to produce rich internet applications and GUI applications with intense graphics that can run consistently over multiple platforms. The subsequent figure displays the complete architecture of the JavaFX platform. Here you can examine the elements that supports JavaFX API. As we can see in the figure here, JavaFX architecture comprises many different components. JavaFX components are briefly described as follows. JavaFX API, the topmost layer of JavaFX architecture, holds a JavaFX public API that implements all the required classes that are capable of producing a full features JavaFX application with rich graphics. The list of all important packages of this API is as follows. JavaFX.animation. It includes classes that are used to combine transition based animation such as fill, fade, rotate, scale, and translation to the JavaFX nodes. Collection of nodes make a scene graph. JavaFX.css. It comprises classes that are used to append CSS like styling to JavaFX GUI applications. JavaFX.geometry. It contains classes that are used to represent 2D figures and execute methods on them. JavaFX.scene. This package of JavaFX API implement classes that interfaces to establish the scene graph. In extension, it also renders sub-packages such as canvas, chart, control, effect, image, input, layout, media, paint, shape, text, transform, web, etc. These are diverse elements that sustain this precious API of JavaFX. JavaFX.application. This package includes collection of classes that are responsible for the life cycle of JavaFX application. JavaFX.event. It includes classes and interfaces that are used to perform and manage JavaFX events. JavaFX.stage. This package of JavaFX API accommodates the top-level container classes used for JavaFX application. Scene graph. A scene graph is the starting point of the development of any GUI application. In JavaFX, all the GUI applications are made using scene graph only. The scene graph includes the primitives of rich internet applications that are known as nodes. In simple words, a single component in a scene graph is known as a node. In general, a scene graph is made of a collection of nodes. All these nodes are organized in the form of a hierarchical tree that describe all the visual components of the application's user interface UI. A node instance can be appended to a scene graph only once. The nodes of the scene graph can have numerous segments like effects, opacity, transforms, event handlers, application specific states. The nodes are of three general types. These are as follows. Root node. A root node is a node that does not have any node as its parent. Leaf node. A leaf node is a node that does not contain any node as its children. Branch node. A branch node is a node that contains a node as its parent and also has a node in its children. Quantum Toolkit. Quantum Toolkit is used to connect Prism and Glass windowing tools, toolkits collectively, and makes them prepared for the above layers in the stack. In simple words, it ties Prism and GWT together and makes them available to JavaFX. Prism in the graphics of the JavaFX applications are based on the hardware accelerated graphics rendering pipeline, commonly known as Prism. Prism engine supports smooth JavaFX graphics that can be executed swiftly when utilized with background graphics card or graphics processing unit GPU. In the situation where the system does not contain graphic cards, then the Prism engine default to the software rendering stack. To interpret graphics, Prism practice DirectX 9 on Windows XP and Vista, DirectX 11 on Windows 7, OpenGL on Mac and Linux embedded systems. Glass Windowing Toolkit. Glass Windowing Toolkit, or simply Glass, is a platform-dependent layer that assists in connecting the JavaFX platform to the primary operating system OS. Glass Windowing Toolkit is very useful as it provides services such as controlling the windows, events, timers, and surfaces to the native operating system. Web view. JavaFX applications can also insert web pages. To embed web pages, WebView of JavaFX uses a new HTML rendering engine technology known as WebKit HTML. WebView is used to make it possible to insert web pages within a JavaFX application. JavaScript appearing in WebView can call Java APIs and vice versa. This element promotes different web technologies like HTML5, CSS, JavaScript, DOM, and SVG. Using WebView, we can execute the HTML content from JavaFX application and can also implement some CSS styles to the user interface UI part of the application. Media engine. Like the graphics pipeline, JavaFX also possesses a media pipeline that advances stable internet multimedia playback at low latency. This high-performance media engine or media pipeline is based on the multimedia frameworks known as GStreamer. By applying the media engine, the JavaFX application can support the playbacks of audio and video media files. The package javafx.scene.media covers all the classes and interfaces that can provide media functionalities to the JavaFX applications. Here you can see a JavaFX API and a scene graph. Below those you can see a Quantum Toolkit. Below that you can see a JavaFX graphics engine, Prism, Win32, GTK, Glass, OpenGL, D3D, WebView, WebKit, Media, GStreams are inside JavaFX graphics engine. Below JavaFX graphics engine, you can see JDK API and tools. Below that, you can see a Java virtual machine. Here you can see structure of a typical JavaFX FXML applications. This figure shows the structure of a typical JavaFX FXML application. As depicted in the figure, the user interface of FXML application is defined inside the FXML document, and all the logic all the logic to handle input events are written inside the controller class. Execution of the program begins with the main class, which invokes the fxml loader. fxml loader passes the fxml document instantiate the nodes specified in the document and build the scene graph. After building the scene graph, fxml loader instantiates the controller class, injects fields defined in the controller class with object instantiated from the fxml documents, and then calls the controller's initialize method. Here you can see main program is connected to XML loader via invokes. Here fxml loader is connected to fxml document via passes fxml document and builds the scene graph. Here fxml, you can see the fxml document defines the user interface and the controller. Here fxml loader is connected to fxml controller via instantiates controller, perform field injection and calls controller's initialize method. Here fxml document is connected to fxml controller via defines. fxml controller here handles mouse and keyboard events. Here you can see the build process for JavaFX application. This diagram explains the flow of the build process for JavaFX application. JavaFX applications and preloaders are packaged into separate jar files, separate jar archives, and so are presented separately in the diagram, but flow is the same. Main application and preloaders consist of source code, style sheets, and other resources. Source code must be compiled, and style sheet can optionally be converted to the binary format. The source code and style sheet and other resources are combined to create a jar archive, which can optionally be signed and have a certificate attached. For web applications, the deployment descriptor JNLP file is prepared to produce the final package consisting of one or more executable jar files, the deployment descriptor, and a web page with the embedded application or a link to launch web start application. To produce the web page, it is possible to use an input template with variables. The build process for JavaFX applications extend the normal build process with several additional steps as outlined in this figure. New or modified steps are marked with colored arrows as described as follows. Optional converts style sheets to binary form. Create jar. Packages code and resources needed for the JavaFX application into a jar file and embeds the utility classes to support auto detection of JavaFX runtime, launch on double click, and integration with the preloader jar if needed. Optional, sign the jar files. Signing jar files is needed only when the application requires elevated privileges such as accessing files on the local file system or accessing non-secure system properties. Signing is not a new concept, and you can sign the jar files for your JavaFX application in the same way as you would for Swing AWT applications. JavaFX runtime supports a new method to sign jar files that reduces the jar size overhead for signing, thereby improving download time. Run the deployment tasks. Assembles the application package for redistribution. By default, the deploy task will generate the base application package, but it can also generate self-contained application packages if requested. The JavaFX packaging tools. The recommended way to package JavaFX application is to use collection of ant tasks and-javafx.jar provided with the JavaFX SDK and also with JDK 7 update 6 or later. NetBeans IDE uses these ant tasks to package JavaFX projects. Embedded packaging support in NetBeans IDE covers most of the typical use cases. However, if you need to send something special, you can always tune packaging by adding custom packaging hooks to the build.xml file, for example as a -post-jar target. Most of the other popular IDEs can easily use custom and built scripts. Other popular build frameworks, for example Maven and Gradle, supports integration with Ant also. JavaFX SDK and JDK 7 update 6 or later include command line packaging utility JavaFX Packager, which can be used for simple packaging tasks. Note that JavaFX Packager is a convenient utility that does not provide as much flexibility or as many options as Ant tasks. Note that JavaFX Packager also provide a -make call macro command to create a complete application package for simple application. The task convert any CSS files to binary format. JavaFX Packager library and task is fx: CSS to bin. JavaFX Packager tool command is JavaFX Packager -create BSS. In NetBeans packaging category, in project properties, select binary encode JavaFX CSS files checkbox. Create jar archive. JavaFX Packager library and task is JavaFX: jar. JavaFX Packager tool command is JavaFX Packager -create jar. In NetBeans IDE occurs by default with the build command using configuration in build projects. Assign a Java archive as one binary project. JavaFX Packager library and task JavaFX is JavaFX -sign jar. JavaFX Packager tool command is JavaFX Packager -sign jar. NetBeans IDE in NetBeans IDE deployment category in project properties, request unrestricted access checkbox to attach a certificate, edit, click edit. Assemble application package for deployment. JavaFX package library and task command is JavaFX :deploy. JavaFX package tool command is JavaFX package -deploy. In NetBeans IDE, base application package is produced by default with the build command. Style sheet conversion. Converting style sheet to binary format is optional but improves application performance. This is especially noticeable on larger CSS files. Usage and task convert CSS files to binary. JavaFX package tool create BSS command in the JavaFX package reference. NetBeans IDE in packaging category of project properties, select binary encode JavaFX CSS files. Create main application Java file. In addition to the application classes and resources, you can provide the information. You can provide the following information when you create main application Java file: platform requirements, required versions of Java runtime and JavaFX runtime, any required Java VM argument, following details about the application, name of the main application class required, class required property, required one, name of the preloader class, if there is a preloader, name of the fallback classes to use if the platform does not support JavaFX, details about the application resources if applicable, a set of class files and other resources including the Java file, list of auxiliary Java files needed by the application including custom preloader Java file if needed. To use the JavaFX packaging tools to create the main application, application Java file is very important for packaging double clickable JAWS and self-contained application. The main application Java file will include the launcher program that takes care of bootstrap launch. This also improves launch by checking for JavaFX runtime, guiding the user through any necessary installations, setting the system proxy for your application. Note, if you have a preloader shown in this figure, create a separate Java file with the preloader resources using any packaging tools listed. Tools. Usage and task is fx :Java. In JavaFX package tool is -create Java command. In NetBeans IDE, handle automatically when you specify this information in the project properties. Sign the Java files. Before adding code to sign your application, ensure that signing is needed because it's carried the cost of overhead to perform validation and often causes additional dialog boxes to be shown to the end user on the application startup. If you want to use traditional methods to sign Java files, consult the Java tutorials steps for code signing and description of the standard and sign Java tasks for installation about traditional signing method. JavaFX also provide a new signing method that helps to reduce the size overhead of signing the Java file. In this method, you sign Java files as one large object instead of signing every Java entry individually. This saves up to 10% of total Java size. To use the signing method provided by JavaFX, you need key store and signing key. The usage and task is fx :signJava. JavaFX package tool -signJava command in the JavaFX package reference. In NetBeans IDE users enable signing when they request elevated permissions for the application by selecting the request unrestricted access checkbox in the properties, project properties. To sign the specific certificate, click edit next to the checkbox. Note, all Jar files must be signed or unsigned in the context of a single deployment descriptor file. If you need to mix signed and unsigned Jar file, use an additional JavaFX deploy and task to generate an additional deployment descriptor for each Jar file. These additional deployment descriptors are called extension descriptors. Use fx resources to refer to the extension descriptors when the main descriptor is generated. Run the deploy task or command. The basic redistribution package consists of the following items: the main executable jar file, optional a set of auxiliary jar files including a jar file with preloader code, deployment descriptor defining how to deploy the application, either basic HTML file with simple code to embed the application into your own web page, or a custom web page that is a result of pre-processing an HTML template. JavaFX packaging tools can also package the application as a self-contained application bundle. This is an opt-in scenario and it is disabled by default. To assemble the redistributable package, you can use one of the following ways: antask fx deploy, JavaFX packaging tool -deploy command in the JavaFX packager reference. In NetBeans IDE, a redistributable package is created every time you build the project. Packaging options are set in the project's properties. Configure the deployment descriptor. The key part of this task is to providing information to the to fill the deployment descriptor for web deployment. This information includes entry points, the main application class, preload class, and other details defined as attributes of the fx application tag. Parameters to be passed to the application defined using fx param and fx HTML param tags under fx application. The preferred application stage size. It is crucial to reserve the display area for embedded content. Width and height are defined using width and height attributes in the fx deploy tag for antask. The JavaFX packager -deploy command in the JavaFX packager tool or in run category of NetBeans project properties. The description of an application to be used in any dialog boxes that the user sees during application startup, defined using the fx info tag. Next point, platform requirement, including required version of the Java and JavaFX runtimes and JVM settings, defined using fx platform tag. Next point, desktop integration preferences of the application, such as adding a shortcut to the desktop or a reference to the startup, defined using optional fx preferences. Permissions. Next point, permissions needed to run the application. By default, the web application run in the sandbox. To request elevated permissions, use the fx permissions tag. Note that in order for the permissions to be granted, application jar files must be signed, and the user must trust the security certificate used for signing. If the application requests elevated permissions but requirements for the user granting permissions are not met, the application will fail to launch. Application resources. The supported application resources. Supported application resource files include jar files, native jar files, JNLP files, icons, license files, data files. Every resource has additional metadata associated with it, such as operating system and architecture for which this resource is applicable, plus a priority preference defining the point in the application lifecycle at which the resource is needed. Careful use of metadata may have a significant impact of the application startup experience. All files in the resource set will be copied to the build output folder. However, not all of them are used in the execution modes. Regardless of the execution mode, all regular Java files from the resource set will be added to the application class path. Native Java files and JNLP files are only used for web deployment. Additional JNLP files are typically used to refer to the external JNLP extension, or if the application itself is packaged as a set of components. Native Java files are used to deploy native libraries used by the application. Each native Java file can contain a set of native dynamic libraries and is inherently platform specific. License files are currently applicable to self-contained application only and are used to add a click-through license to installation packages. Data files do not have special semantics and applications are free to use them for anything. For example, if your application needs a bundle of movie file, then you can mark it as a data and it will be included in the application package. Package custom JavaScript actions. Deployment Toolkit provides a set of hooks that can be used to customize the startup behavior when an application is deployed in the browser. Developers must install the callback function to the hook and it will be utilized by the deployment toolkit. However, in order to ensure that they are correctly installed, they also must be specified at packaging time. To specify callback, list them in the fx::callbacks tag on the fx::deploy. Add an fx::callback entry for every callback you want to install and specify the name of the hook in the name attribute. The content of fx::callback tag is the JavaScript function to be used. You can use a full function definition or refer to a function defined elsewhere. Usage and task fx::callback. JavaFX packager tool, see -deploy command in the JavaFX packager reference. NetBeans ID, add callback in the deployment category of project properties. Click the edit button to the right custom JavaScript actions. Web page templates. By default, JavaFX packaging tools generate a simple web page with the placeholder for the embedded application. You can manually copy code from this generated page to your real web page, but this is error prone and time consuming if you need to do this often. JavaFX packaging tool also support injecting required code into an existing web page through the use of an input template. This is especially useful when the application is tightly integrated with the web page. For example, if the application uses JavaScript to communicate to the web page, or if the callbacks are used and their code is kept in the web page itself. The usage and task, add the template tag. JavaFX package tool -deploy command in the JavaFX packager reference. In NetBeans ID, specify the input HTML file in the run category of the project properties. Passing parameters to the application. JavaFX application supports two types of application parameters, named and unnamed. Static name parameters can be added to the application package using fx::param, and unnamed parameters can be added using fx::argument. They are applicable to all execution modes, including standalone applications. It is also possible to pass parameters to a JavaFX application from a web page that hosts it using fx::HTML param. Prior to JavaFX 2.2, this was only supported for embedded applications. Starting from JavaFX 2.2, JavaFX colon HTML param is applicable to web start application also. Passing parameters to the HTML page is the most useful if parameters are dynamic. To use this technique, we recommend the following approach. Use a web page template to provide JavaScript code to prepare dynamic preferences. Pass a JavaScript snippet as a value for fx colon HTML param and specify escapes equal false. Then it will be evaluated at runtime. Customizing JVM setup. You can specify required JVM options and set the properties using fx colon JVM mark and fx colon property tags at your end task. These tags are applicable for all execution modes except standalone applications. In other words, you always get a default JVM if you double click at the jar file, but you can tailor the JVM to your requirement if you are running a self-contained application. A web start application or an application embedded into a web page. Packaging complex applications. Real life applications often have more than just a single jar artifact. They may have third-party libraries, data files, native codes, and so on. For the complex application, you may need this special packaging to support different execution modes. There are too many possible scenarios to cover all cases, but here are some guidelines. Mark platform-specific resources accordingly. For the double clickable jar file, consider repackaging everything into a single giant jar file and loading native libraries and data files from inside the jar. Alternative, if you prefer to have multiple files, make sure all dependent jar files are listed in fx colon resources tag in the fx jar colon jar task that will create the main jar. List all the jar files and libraries in file sets with type equal data to copy them into output folder. Load native libraries and resources from locations relative to the main jar file. Self-contained applications. For self-contained applications, avoid packaging anything but the main jar file using fx jar fx colon jar. Multiple embedded launchers can confuse the native launcher. List all dependent jar files in the fx colon resources section of fx colon deploy and fx colon jar for the main application jar file. Either use explicit location relative to the application jar file to load native libraries or copy native libraries to the root application folder. For web start and embedded application, list all dependent jar files in the fx colon resources section of fx colon deploy. Native libraries should be wrapped into the jar files for redistribution. Use one jar file per platform. Ensure jar files contain native libraries only and that the libraries are all on top of on top level folder for the jar file. Publishing an application that fills the browser window. Prior to JavaFX 2.2, it was not an easy to size embedded application relative to the size of the web browser window. The width and height attributes of the fx colon deploy task can only take numerous values because they are used not to just generate HTML JavaScript code but also the deployment descriptor. In JavaFX 2.2, the two new attributes were added: fx colon deploy task, embedded width and embedded height. These attributes enable you to specify the size relative to the browser window, for example 50%. Performance tuning for web deployment. There are several options that can be used to improve application launch time for the first and subsequent launches of the web application. One background update check for the application, embedded deployment descriptor into the web page, embedded signing certificate into the deployment descriptor, and use new JavaFX signing method, signed applications. Here you can see application, source code, CSS style sheets and other resources, images, etc. inside application here. Source code is connected to the compile code. Compile code is connected to create jar. Here CSS style sheets are connected to binary CSS via convert to binary, and binary CSS is connected to create jar. Here source code, CSS style sheets and other resources, image etc. Images etc. are in preloader. Source code is connected to compiled code, and CSS style sheets are connected to binary CSS via convert to binary, and create jar here and here are connected to this section. Here executable application jar, sign jar is connected to it, and here preloader jar, sign jar is connected to it. This goes with the deploy. Here additional libraries and resources are connected to deploy. Here web page template is connected to deploy. Here deploy is connected to base packages, base package, main executable jar, preloader jar, other libraries, and deployment descriptor JNLP, and web page are inside base package. Here the self-contained application bundle, application JavaFX runtimes, native live launcher, here exe, dmg, etc. Here you can see life cycle of a JavaFX application. There are in total 3 lifecycle methods of JavaFX application class. These methods are start. The start method is the entry point method of the JavaFX application, where all graphics code of JavaFX is to be written. Init, the init method is an empty method that can be overridden. In this method, the user cannot create a stage or scene. Stop, the stop method is an empty method that can also be overridden, just like the init method. In this method, user can write the code to halt the application. Other than these methods, JavaFX application also implement the static method known as launch. This launch method is used to launch the JavaFX application. As stated earlier, the launch method is static, and the user should call it from the static method only. Generally, the static method, which calls the launch method, is the main method only. Whenever a user launches an JavaFX application, there are few actions that are carried out in a particular manner only. The following is the order given in which a JavaFX application is launched. 1. Firstly, the instance of an application class is created. 2. After that, the init method is called. 3. After the init method, the start method is called. 4. After that, after calling start method, the launcher wait for the JavaFX application to end, and then calls the stop method. Here public void init method in class application package javafx.application module javafx.graphics. The application init method This method is called immediately after the application class is loaded and constructed. An application may override this method to perform initialization prior to the actual starting of the application. Here the public abstract void start stage, primary stage. This method, the main entry point for all JavaFX applications. The start method is called after init method has returned, and after system is ready for the application to begin running. Not this method is called on JavaFX application thread. Public void stop. This method is called when the application should stop and provide convenient place to prepare for application exit and destroy resources. If we revise the application, revise the life cycle, the entry point for JavaFX application is the application class. JavaFX runtime does the following in order whenever the application is launched. One, start the JavaFX runtime if not already started. Two, construct an instance of the specified application class. Three, calls the init method. Four, calls the start javafx.stage method. Five, wait for the application to finish, which happens when either of the following occur. Point the application calls platform.exit. Next point, the last window has been closed and the implicit exit attribute on platform is true. 6, calls the stop method. Note that the start method is abstract and must not be overridden. The init and stop methods have concrete implementation that do nothing. Application subclass must be declared public and must have a public no argument constructor. Calling platform.exit method is preferred way to explicitly terminate a JavaFX application. Directly calling system.exit int is an acceptable alternative but doesn't allow the application stop method to run. A JavaFX application should not attempt to use JavaFX after the FX toolkit has terminated or from a shutdown hook, that is after a stop method returns. So system.exit int is called. Note the JavaFX classes must be loaded from a set of named JavaFX.asterisk modules on the module path. Loading the JavaFX classes from the class path is not supported. Here you can see the main string array args method is connected to init method. Init method is connected to start stage method. Start method is connected to stage.show method here. Show method is connected to stop method here. Here you can see configuration dialogues and generated project here. We are now considering application creator. On top of this is a sample of with regarding custom application plugin to generate seed application and views based on predefined set of templates. It is tailored to CERN here environment, suggesting project and Java package name following our convention as well as corresponding location of SVN repository. The developer just types the project name and select one of the available templates. The plugin then generates a ready to run JavaFX project with proper structure and configured set of core dependencies. Different templates can contain sample applications that vary in level of complexity and applied pattern. The simplest is one page hello world application with just a single FX simple FXML corresponding controller and CSS file. Other samples contain 2 or more views and demonstrate different ways of interactions between them and with external services. All of the templates follow the project structure and naming conventions. They also contain corresponding test classes for both the classical unit test of the controller and the test FX test classes. Here you can see Xsoft app optimizer. Inside it, source Java, source src resources as the test, and src and product.xml and project.properties file. Here inside src Java, you can see the package cern.xsoft.app.optimizer. Inside it, the package detector and the classes. Here you can see the file detector controller.java, detector model.java, and detector.css, detector.fxml, and inside cern.app xsoft.app optimizer package, optimizer app Java, optimizer controller Java, optimizer model.java, optimizer.css, optimizer.fxml. Inside src test, you can see the package cern.xsoft.app.optimizer. Inside it, optimizer app test.java, optimizer controller test Java. So here you can see the sample directory structure here. Now we are focusing on JavaFX public APIs and scene graph. JavaFX public APIs, the top layer of the JavaFX architecture, provides a complete set of public APIs that support rich client application development. These APIs provide unparalleled freedom and flexibility to construct rich client applications. The JavaFX platform combines the best capabilities of the Java platform with comprehensive immersive media functionality into an intuitive and comprehensive one-stop development environment. Scene graph. The JavaFX scene graph is the starting point for constructing a JavaFX application. It is a hierarchical tree nodes that represent all of the visual elements of the application's user interface that can handle it can handle input and can be rendered. Here you can see JavaFX application lifecycle. The entry point for JavaFX applications is the application class. The JavaFX runtime does the following in order whenever an application is launched. 1. Construct an instance of the specified application class, calls the init method. 3. Step 3 calls the start JavaFX.stage method. Stage 4 wait for the application to finish, which happens when either of the following occur. The application calls platform.exit method. The last window has been closed and the implicit exit attribute on platform is true. Step 5 calls the stop method. Note that start method is abstract and must be overridden. The init and stop methods have concrete implementations that do nothing. Calling platform.exit method is the preferred way to explicitly terminate a JavaFX application. Directly calling system.exit int method is an acceptable alternative but doesn't allow the application stop method to run. A JavaFX application should not attempt to use a JavaFX after the FX toolkit has terminated or from a shutdown hook, that is after the stop method returns or system.exitInt method is called. Here you can see launch is connected to init and init is connected to start and start is connected to stop. Here you can see root, branch and leaf nodes. This figure shows a general inheritance diagram of root, branch and leaf nodes. The root node has 2 leaf nodes and 1 branch node. The branch node has 2 leaf nodes. The JavaFX Scene Graph API makes graphical user interface easier to create, especially when complex visual effects and transformations are involved. A scene graph is a tree data structure most commonly found in graphical applications and libraries such as vector editing tools, 3D libraries, and video games. The JavaFX Scene Graph is a retain mode API, meaning that it maintains an internal model of all graphical objects in your application. At any given time, it knows what objects to display, what areas of the screen need to repainting, and how to render it all in the most efficient manner. Instead of invoking primitive drawing methods directly, you instead use the Scene Graph API and let the system automatically handle the rendering details. This approach significantly reduces the amount of code that is needed in your application. The individual items held within the JavaFX scene graphs are known as nodes. Each node is sorry. Each node is classified as either a branch node, meaning that it can have children, or leaf node, meaning that it cannot have children. The first node in the tree is always called the root node, and it never has a parent. Here you can see the root node here, and root node is connected to leaf nodes and a branch node here, and branch node is connected to leaf nodes here. Here you can see the scene graph consists of a window, stage, scene and its nodes. A scene describes everything that is inside a window in a JavaFX application, where the window provides a look and feel that's specific to the OS that's driving the application. The scene is completely yours to style and change. The window that most people will use is a stage, which extends the window class. Each of these concepts, stage, scene graphs, and nodes, surround the scene object, and together they discharge the responsibility of rendering your application to the screen. Stage. The stage represents the window of any view in the JavaFX model. In fact, it extends the window. Scene graph. The scene graph in JavaFX represent the contents of a scene that focuses on the hierarchical relationship between nodes. Prism rendering scene graph. Alongside the scene graph, we get to see and modify. JavaFX maintains a sister scene graph and uses this to determine almost other things. How much of the scene has changed and which areas of the scene need updating. The textures required to render the scene, and the rendering of the scene. Part of the reason that the JavaFX scene can be so efficient is that it caches and unchanged elements of a scene, so they don't need to be recomputed unnecessarily. Nodes are the foot soldiers of a user interface. From charts to images, layouts to shapes, they all extend the node class in some way. The node is the basic interface component that has bounds, layout position, event handling, mouse, keyboard, etc., opacity and transforms. All other UI elements layer functionality on top of the node class. Scene is responsible for 4 things: holding a reference to the parents that hold the scene nodes, that is most often a layout of some type, but can be a group. Optionally controlling the size of the window that can be delegated to the root node, but doesn't have to be. Setting default higher level rendering properties, useful for 3D scenes and the camera also for 3D. Triggering event handling behind the scenes. For each of these things impacts how the scene works and how it needs to be defined. For instance, because the scene will hold your scene graph, it must to be defined with the root node. Anti-aliasing and depth testing corresponds to higher level rendering properties, which can be set as default for this the scene. Here you can see nodes must belongs to a group or layout parents. Nodes are connected to scene. Nodes interacts with scene. Scene holds all nodes in a parent and directs events. Scene interacts with stage. Stage extends window, handles UI centric styling and behavior. Here you can see a JavaFX scene graph. A scene graph is a tree data structure that arranges and groups graphical object for easier logical representation. It also allows the graphics engine to render the object in the most efficient way by fully or partially skipping object which will not be in the final image. The following figure shows an example of a JavaFX scene graph architecture. At the very top of the architecture is a stage. A stage is a JavaFX representation of a native OS window. At any given time, a stage can have a single scene attached to it. A scene is a container for the JavaFX scene graph. All elements in the JavaFX scene graph are represented as nodes, as node objects. There are 3 types of nodes: root, branch, and leaf. The root node is the only node that doesn't have a parent. and is directly contained by a scene, which can be seen in the figure here. The difference between branch and a leaf is that a leaf node does not have children. In the scene graph, many properties of a parent node are shared by the child nodes. For instance, a transformation or an event applied to a parent node will also be applied recursively to its children. As such, a complex hierarchy of nodes can be viewed as a single node to simplify the programming model. Here you can see a stage. Native window interacts with scene interacts with root node interacts with leaf nodes, and branch node. Here branch node interacts with leaf nodes. Here you can see the module structure. Here we focuses on the JavaFX user-facing programming interface. All standard components, controls, and other auxiliary classes are organized as standard JPMS module since Java 9. Each module defines its build dependencies. For instance, JavaFX.base package is always imported by all other JavaFX modules. The module structure allows separating platform-specific functionality. For example, iOS, x86 PC, and heavyweight extra controls not required by every type of application. For example, web browser, media player. Note, while the AWT and previous AWT and Swing frameworks are included in the standard Java distribution, for example, OpenJDK, JavaFX has been distributed as a separate project since Java 9. The most obvious sequence of this is having a build configuration is practically required, while previously just importing the GUI classes was sufficient. Since the OpenJFX 16, even loading JavaFX classes using legacy class path is discouraged. Thus, the easiest way to package JavaFX programs is by using build system and JavaFX plugin. Next, we will discuss. We will take a bit more detailed look at each module. JavaFX.base. The base module contains classes related to reactive programming, event handling, and miscellaneous auxiliary classes. For example, the type for time durations. These classes are essential for event-based and asynchronous programming in general. JavaFX.beans.asterisk wrappers for reactive values and handling of values. JavaFX.collections.asterisk wrappers for collections with reactive properties react to operate such as insertion or deletion. JavaFX.event.asterisk generic event handling infrastructure. JavaFX.util.asterisk helpers and transformers, for example, duration. JavaFX.controls. The control module contains a standard set of 208 plus active component for forms. JavaFX.scene.chart.asterisk special components for data visualization, for example, bar or pie chart. JavaFX.scene.control.asterisk standard components extend scene.control.control, visual representation implement scene.control.skin. Some more geared towards model view control MVC paradigm. For example, the ones with model in the class name. Typical class hierarchy for controls: object, then scene.node, then scene.parent.scene. Then scene.layout.region, then scene.control.control, then component X. Visit the API documentation or play around with scene builder to find visual example for components. Common ID with auto completion help a lot when writing controller code for the component. Note some component employ generic types to ensure safe access to data. Due to the way generics are implemented in Java, generic types should not be nested. For example, type A, then less than sign, then type B, then type C, as the compiler cannot guarantee correct behavior for these values at time. If there is a need for generic nested generic types, simply create a new class that extends from that type. In generic, static types in Java do not prevent incorrect use of null values, but can eliminate other incorrect use of types. In Kotlin, even incorrect uses of null values can be eliminated. JavaFX.fxml. The fxml module contains classes for interfacing with fxml files built with scene builder. At fxml, annotation for exposing a private protected member in controller class to the fxml routines. Fxml loader, used for loading .fxml files, instantiating the scene and building to a controller. JavaFX.graphics. The graphics module contains a standard set of classes. One, manipulating the scene graph, for example, layout, forms, transformation, painting, image and pixel manipulation, effects, printing, animations, etc. etc. JavaFX. Animation, CSS, geometry. JavaFX.print, print into a paper. JavaFX.scene, general purpose classes plus cameras and lights. JavaFX.scene.effect or paint, theming and visuals. JavaFX.scene.canvas or image or shape or text, graphics element. JavaFX.scene.input, event handling, concrete event types. JavaFX.scene.robot, UI testing. JavaFX.scene.layout. 2, dealing with windows, dialogues and scenes, window contents. JavaFX.application plus others. JavaFX.stage.file chooser, pop-up, scene, stage, window plus others. 3, coordinating concurrent task. JavaFX.concurrent task service worker. JavaFX.media. The media module contains the standard set of classes for the playback of video and audio, audio clip, playback of audio, audio equalizer, graphic equalizer, media resources, media player, playback controls, media view components, dash track components, handle the distinct streams of sound, video and subtitles etc. in a media file or source. JavaFX.swing. The swing module provides the compatibility layer for the legacy swing AWT code. The main purpose of these classes is to either enable the use of old component in a JavaFX application or to support extending a legacy application with new component. JFX panel, for displaying JavaFX content in a Swing app. Swing FX utils, tools for transforming between, for example, different bitmap formats. Swing node, for displaying swing contents in a JavaFX app. JavaFX.web. The web module contains a set of WebKit based component for displaying web component in JavaFX application. HTML editor, web engine, background object manages the web page and session. Web event, web specific event. Web view, the visual control component for displaying the web content. Monocall, the default graphics pipeline backend will refuse to launch a JavaFX in, for example, GTU's GitLab CI/CD. In order to run JavaFX programs headless, the monocall framework is required. Here the module JavaFX.base defines the base API for the JavaFX UI toolkit, including APIs for binding, properties, collections, and events. Here the JavaFX module JavaFX.graphics defines the core scene graph for defines the core scene graph APIs for JavaFX UI toolkit, such as layout, containers, application lifecycle, shapes, transformations, canvas, input, painting, image handling, and effects, as well as API for animation, CSS, concurrency, geometry, painting, and windowing. Note the JavaFX classes must be loaded from the set of named JavaFX.asterisk modules on the module path. Loading the JavaFX classes from the class path is not supported. Module JavaFX.media defines APIs for playback of media and audio content as part of the JavaFX UI toolkit, including media view and media player. Module JavaFX.swing defines the APIs for JavaFX swing interop support included with the JavaFX UI toolkit, including swing node for embedding swing inside the JavaFX application, and JavaFX panel for embedding JavaFX inside the swing application. Module JavaFX.control defines a UI control chart and skins that are available for JavaFX UI toolkit. Module JavaFX.web defines APIs for web view functionality contained within the JavaFX UI toolkit. Module JavaFX.fxml defines the fxml APIs for JavaFX UI toolkit. Here JavaFX media is connected to JavaFX base. Here JavaFX media is connected to JavaFX graphics. Here JavaFX swing is connected to JavaFX.graphics, and JavaFX.web is connected to JavaFX graphics and JavaFX base and JavaFX.control. Controls JavaFX.controls is connected to JavaFX graphics and JavaFX base. JavaFX.graphics is connected to JavaFX base. Here JavaFX.fxml is connected to JavaFX.base. Now we are considering JavaFX application structure. JavaFX application is divided hierarchically into the three main components known as stage, scene, and nodes. We need to import JavaFX.application class in every JavaFX application. This provides the following lifecycle method for JavaFX application: public void init method, public stack void start stage primary stage method, public void stop method. In order to create a in order to create a basic JavaFX application, we need to import JavaFX.application into our code, inherit application into our class, override start method of application class. Stage is stage in a JavaFX application is similar to a frame in a Swing application. It acts like a container for all JavaFX objects. Primary stage is created internally by the platform. Other stages can further be created by the application. The object of primary stage is passed to start method. We need to call show method on the primary stage object in order to show our primary stage. Initially the primary stage look like however, we can add various objects to this primary stage. The objects can be added in a hierarchical way. That is, first scene graph will be added to this primary stage, then and then that scene graph may contain nodes. A node may be any object of the user's interface, like text area, button shapes, and text area, button shapes, media, etc. Scene actually hold all the physical contents, nodes. of the JavaFX application. Scene class provide all the methods to deal with the scene object. Creating scene is necessary in order to visualize the content of the stage. At one instance, a scene object can only be added to one stage. In order to implement scene in our JavaFX application, we must import JavaFX.scene package in our code. The scene can be created by creating the scene class object and pass the layout object into the scene class constructor. Scene graph. Scene graph exists at the lowest level of the hierarchy. It can be seen as the collection of various nodes. A node is an element which is visualized in the stage. It can be any button, text box layout, image, radio button, checkbox, etc. Nodes are implemented in a tree kind of structure. There is always one root in the scene graph. This will act as a parent node for all other nodes present in the graph. However, this node may be any of the layout. This node may be any of the layouts available in the JavaFX system. Leaf nodes exist at the lowest level in the hierarchy. Each of the node present in the scene graph represent the classes of JavaFX.scene package. Therefore, we need to import the package into our application in order to create a full featured JavaFX application. Class stage. The JavaFX stage class is the top level JavaFX container. The primary stage is constructed by the platform. Additional stage object may be constructed by the application. Class scene. The JavaFX scene class is the container for all content in a scene graph. The background of the scene is filled as specified by the fill property. Class node in a package JavaFX.scene. Base class for scene graph nodes. A scene graph is a set of three data structures where every item has a 0 or more parents, and each item is either a leaf with 0 sub items or a branch with 0 or more sub items. The class shape 3D in package JavaFX.scene.shape. The shape 3D base class provides definitions of common properties for objects that represent some form of 3D geometric shapes. These properties include the material to be applied to the fillable interior of the shape or the outline of shape. And next point, the draw model properties that define how to render its geometry. Next point, the face culling properties that defines which face to cull. Note that this is a conditional feature. Class parent, the base class for all nodes that have children in the scene graph. The class region in package JavaFX.scene.layout. The region is a base class for all JavaFX node-based UI controls and all layout containers. It is a resizable parent node which can be styled from CSS. It can have multiple backgrounds and borders. It is designed to support as much of the CSS3 specification for backgrounds and borders as is relevant to JavaFX. The full specification is available at the W3C. Class pane in package JavaFX.scene.layout. The base class for layout panes, which need to expose the children list as public so that users of the subclass can freely add or remove children. Class control in package JavaFX.scene.control. The base class for all user interface controls. A control is a node in the scene graph which can be manipulated by the user. Controls provide additional variables and behaviors beyond those of the nodes to support common user interactions in a manner which consist and predictable to the user. The class shape in package javafx.scene.shape. The shape class provides definitions of common properties for objects that represent some form of geometric shape. These properties include a pane to be applied to the fillable interior of the shape, a pane to be applied to the stroke, the outline of the shape, the decorative properties of the stroke including the width of the border stroke, whether the border is drawn as the interior padding to the edges of the shape as an interior etching edges of the shape as an interior edging of the that follows the inside of the border, or as a wide path that follows along the border striding it equally both inside and outside. Decoration styles for joins between path segment and unclosed ends of path, and dashing attributes. Here you can see the stage here. Scene is inside the stage, and scene graph is inside scene. Inside the scene graph you can see nodes. Root node interacts with branch node, and here leaf node, and branch node interacts with leaf nodes. Here here you can see node contains subclasses 3D shape 3D parents and shapes, and parents contain a subclass region, and region contains subclasses pane and control. Here you can see a CSS style sheet sample. This image contains two screen captures of the same UI controls but with different CSS style sheets applied. The left screen uses the style sheet that defines the background color as gold and the UI control as a lighter gold. The font for the controls is a sans serif font in black. The two custom buttons are oval shaped and light gold color. The first button labeled accept in the green font. The second button is labeled decline in the red font. To the right of the buttons is a label not available. By contrast, the right screen uses a style sheet that defines a background color as light olive and the UI control as a medium olive. The font for the control is a Courier New font in dark gray. In this version of UI, the accept and decline buttons have both standard rectangle shape, but the border of the buttons is a dark gray and the font color is a medium green, and the labels fills the buttons with minimal space between the label and the edge of the button. The not available and progress labels have a dash line border around them. A font of a complete assessment of type of the one size and face includes caps, small caps and lowercase, punctuation marks as accent and commonly used symbols. It contains alphabets in Roman and italic capitals and boldface. Thus, the Courier New typeface is 12 point size is the font, but Courier New is a typeface. Font and typefaces don't come with colors. The color is a function of the printing process. Sans serif and serif are contrasting styles, and proportional and monospace are contrasting styles. JavaFX cascading style sheets (CSS) provide the ability to apply customized styling to the user interface of JavaFX application without changing any of that application's source code. CSS can be applied to any node in the JavaFX scene graph and are applied to the nodes asynchronously. JavaFX CSS styles can also be easily assigned to the scene graph at runtime, allowing the application appearance to dynamically change. This figure demonstrates the application of two different CSS styles to the same set of UI controls. JavaFX CSS are based on the W3C CSS version 2.1 specification, with some additions from the current work on version 3 and newer versions also. The JavaFX CSS support and extensions have been designed to allow JavaFX CSS style sheets to be passed cleanly by any compliant CSS parser, even one that does not support JavaFX extensions. This enables the mixing of CSS style for JavaFX and other purposes, such as HTML pages, into a single style sheet. All JavaFX property nodes names are prefixed with the vendor extension of -fx-, including those that might seem to be compatible with the standard HTML CSS, because some JavaFX values have slightly different semantics. Here you can see a JavaFX UI control sample. The illustration shows a sample UI and JavaFX UI controls. The controls are presented in rows. Each row corresponds to a particular type of UI control. Top row contains 4 buttons. The left button in the row has cancel option, a cancel caption on it. The next button has neither a caption nor a graphics. Third button has both caption and graphics. The fourth button has the cancel caption and is highlighted. The second row shows toggle button. Left toggle button has the first caption on it. The next button has the second caption and looks pressed. The third button has the third caption on it. Fourth button has no caption. The rightmost button in the row has a long description that reads long and really long. Third row contains 2 hyperlinks. First hyperlink has only the textual caption, "Hello, I am a hyperlink." The second hyperlink has both an icon and the text caption, "I have an icon too." Fourth row present 3 checkboxes. Left checkbox is not selected and has the caption, "Hit me dude." The center checkbox is the undefined state and has the caption, "Are you sure?" The right checkbox is the selected state and has the caption, "There you go." Fifth row shows 2 radio buttons. Left radio button is unselected and has a caption "Bye." The right radio button is selected and has the caption "Hello." The sixth row contains menu buttons. The left button has a down arrow that indicates that the menu expands downwards. The right button has the right arrow that indicates that menu expands right side. The seventh row shows the scroll window view component. It presents a scrollable area with both vertical and horizontal scroll bars. Eighth row presents 2 progress bars. First progress bar indicates progress of approximately 25%. The second bar is the indefinite state. Ninth row shows the progress indicator in the intermediate indeterminate state. 10th row present two list view component. The left list view has a vertical scroll bar following elements: item 0, item 1, item 2, item 3, item 4. The second list view has a horizontal scroll bar and list following the element 7, 8, 9, 10, 11. The JavaFX UI controls available through the JavaFX API are built by using nodes in the scene graph. They can take a full advantage of visually rich features of the JavaFX platform and are portable across different platforms. JavaFX CSS allows for theming and skinning of the UI controls. This figure shows some of the UI controls that are currently supported. New Java UI controls like title pane or accordion have been introduced with the JavaFX SDK. The new controls reside in the javafx.scene.control package. For more details, doc information about all the available JavaFX UI controls, see JavaFX UI controls document in the API and the API documentation for the javafx.scene.control. The class button, a simple button control. Button control can contain text or a graphic. Button control has three different modes: normal push buttons, default. The default button is rendered differently to make the apparent to users that there should be the default choice should be. They can be unclear as to what should be selected. The behavior of the default button differs depending on the platform in which represented. In Windows and Linux, the default button receives an enter key presses when it has the focus. When the default button does not have the focus is on another button control, the enter key press will be received to the other non-default button. When the focus is elsewhere in the user interface and not on any button, the enter key press will be received by the default button if one is specified, or if no other node in the scene consumes it first. In Mac OS X, the default button is the only button in the user interface that responds to the enter key press. If focus is on another non-default button, the enter is pressed, the event is only received by the default button. On Mac OS, the only way to fire a non-default button is through space key. The cancel button is the button that receives keyboard VK_ESC press if no other node is in the scene consumes it. Toggle button. The class toggle button. The toggle button is a specialized control which has the ability to be selected. Typically, a toggle button is rendered similarity to a button. However, there are two different types of controls. The button is a command button which invokes a function when clicked. A toggle button is, on the other hand, is simply controlled with a boolean indicating whether it has been selected. Class hyperlink, an HTML-like label which can be a graphic and or text which responds to rollovers and clicks. When a hyperlink is clicked or pressed is visited becomes true. A hyperlink behaves just like a button. When a hyperlink is pressed and released, an action event is sent, and your application can perform some action based on this event. Class checkbox. A tri-state selection control typically is skinned as a box with a check mark or tick mark when checked. A checkbox control can be one of three states, checked, indeterminate, false, checked true, intermediate equal false, and checks equal true, unchecked, indeterminate equal false and check equal false, undefined, indeterminate equal true. If checkbox is checked, then it is also it is also by definition defined. When checked, the checkbox is typically rendered with the check or tick mark. The checkbox is in this state is selected is true and indeterminate is false. The class radio button. The radio buttons create a series of items where only one item can be selected. Radio buttons are a specified toggle button. When radio button is pressed and released, an action event is sent. Your application can perform some action based on this event by implementing an event handler to process the action event. Class menu button. Menu button is a button which when clicked or pressed will show a context menu. The menu button shares a very similar APIs to the menu control insofar that you set the items that should be shown in the items observable list, and there is a text property to specify the label shown within the menu button. Progress bar, the class progress bar, and specialization of the progress indicator, which is represented as a horizontal bar. The class progress indicator, a circular controller which is used to indicate for indicating progress, either indefinite, either infinite, also known as indeterminate, or finite, often used with the task API for representing progress of background tasks. A list view, the class list view T. A list view displays the horizontal or vertical list of items from which the user may select or which the user may interact. A list view is able to have its generic type set to represent the type of data in the backing model. Doing this has the benefit of making various methods in the list view, as well as supporting classes mentioned, supported classes type shape. In addition, making use of generic type supports substantially specified development of applications making use of list view, as all modern IDEs are able to autocomplete far more sufficiently with the additional type information. Here you can see buttons, and here toggle buttons and hyperlinks here. Checkbox, normal, undefined and selected. Radio buttons, menu buttons, scroll view, progress bar, progress indicator is indeterminate, list views here. Here you can see a simple JavaFX application. The class application class from which JavaFX applications extend. This class is in package javafx.application. As an example 2, we can consider JavaFX application lifecycle here. Launch a standalone application. This method is typically called from the main method. it must not be called more than once or an exception will be thrown. This is equivalent to launch the class.class args, where the class is the immediately enclosing class of the method that called launch. It must be a subclass of application, or a runtime exception will be thrown. Launch method does not return until the application has exited, either via a call to platform.exit or all of the application windows have been closed. Init. The application initialization method. This method is called immediately after the application class is loaded and constructed. An application may override this method to perform initialization prior to the actual starting of the application. The implementation of this method provided by the application class does nothing. Note, this method is not called on the JavaFX application thread. An application must not construct a scene or a stage in this method. An application may construct other JavaFX objects in this method. Start. This method is called when the application should the main entry point for all JavaFX applications. The start method is called after the init method has returned and after the system is ready for the application to begin running. Note, this method is called on the JavaFX application thread. Stop. This method is called when the application should stop and provides a convenient place to prepare for application exit and destroy resources. The implementation of this method provided by the application class does nothing. Note, this method is called on the JavaFX application thread. Here you can see add an exit button to the scene here. As an example 3, we can consider JavaFX.scene package. Provides the core set of base classes for the JavaFX scene graph API. as an example 4, we can consider adding a leaf node. Class scene, the JavaFX scene class is the container for all the content in a scene graph. The background of the scene is filled as specified by the fill property. The class scene is in JavaFX.scene package. The important points to consider in this example are as follows. The main class is an extension of the JavaFX.application class. Its start method is overridden. In this case, overridden and receives a stage object, a top level GUI container, as its only parameter. The root node, in this case, an instance of the JavaFX.scene.group class is created and passed to the scene constructor along with the scene's width, height, and fill. The stage title scene and visibility are all set. The main method invokes the application.launch method. The blue rectangle leaf node, that is 250 multiplied by 250 pixels, will appear at the specified x and y coordinates. By default, x increases from left to right and y increases from top to bottom. This can be affected by transformations. However, this figure shows the results of adding a leaf node. As an example 5, we can consider this one as adding leaf nodes. Class scene here, the JavaFX scene class is the container for all content in the scene graph. The background of the scene is filled with as specified by the fill property. The the class node is the base class for scene graph nodes. A scene graph is a set of tree data structures where every item has a 0 or 1 parents. And each item is either leaf with 0 sub items or a branch with 0 or more sub items. This scene and node class nodes are in package JavaFX.scene. Here the class circle is a subclass of class shape, and class shape is a subclass of class node. Here the class text is a subclass of class shape, and class shape is a subclass of class node. Here you can see a push integration. Here the method void run later runnable. The run the specified runnable in on the JavaFX application thread at some unspecified time in the future. The push communication is a request response style of communication without the request part. The application server can push out data at any time. The Java Message Service JMS WebSockets and memory grids come with a fire and forget style notification mechanism and can be easily integrated with JavaFX. JSR 356 implements the WebSocket protocol, is a part of Java EE7 and comes with the Java Client API. The WebSocket specification introduces a bidirectional binary protocol and is perfectly suitable for integration of UI clients, WebSocket messages. WebSocket messages can have a binary or text nature and are received with an endpoint subclass as shown here. As an exception example, we can consider this illegal state exception. If this method is called more than once, the method we consider here is void launch string ... args in class application. As an exception example 2, we can consider null point exception. If root is null in constructor scene parent root double width double height boolean depth buffer in class scene. Now we are considering module JavaFX.base defines the base API for the JavaFX UI toolkit, including APIs for binding, properties, collections, and events. As an example 8, we are considering module JavaFX.controls defines the UI controls, charts, and skins that are available for the JavaFX UI toolkit. JavaFX.fxml, the module JavaFX.fxml define the fxml APIs for the JavaFX UI toolkit. Module JavaFX.graphics defines the core scene graph APIs for the JavaFX UI toolkit, such as layout, containers, application lifecycle, shapes, transformation, canvas, input, painting, image handling, and effects, as well as APIs for animation, CSS, concurrency, geometry, printing, and windowing. Note: the JavaFX classes must be loaded from a set of named JavaFX.asterisk modules on the module path. Loading the JavaFX classes from the class path is not supported. Module JavaFX.media defines APIs for playback of media and audio content as part of the JavaFX UI toolkit, including media view and media player. Module JavaFX.swing defines APIs for the JavaFX swing interrupt support included with the JavaFX UI toolkit, including swing node for embedding swing inside a JavaFX application, and JFX panel for embedding JavaFX inside the swing application. Module JavaFX.web defines APIs for the web view functionality contained within the JavaFX UI toolkit. Now we are considering overview in scene graph. One possible implementation will produce a scene graph matching the figure above as follows. Scene class scene in package JavaFX.scene. The JavaFX scenes class is a container for all content in a scene graph. The background of all scene is filled as specified by the fill property. The result of running code is seen in this figure. An example of hello world scene graph can be seen in this figure here. The important nodes: a node can have maximum one parent. A node is the active attached to currently visible scene. Scene graph can only be modified from the JavaFX application thread. Uh, Now we are considering here string converter, complete code in string with the string converter in choice box in UI controls. The code can be tested in a single .java file. The class choice box in package javafx.scene.control in module javafx.controls. The choice box is used for presenting the user with a relatively small set of predefined choices from which they may choose. The choice box, when showing, will display to the user these choices and allow them to pick exactly one choice. When not showing, the current choice is displayed. Here we demonstrate the choice box. The choice box control is a list of values from which the user makes a selection. In this particular implementation, there is an empty value which makes a selection optional. The following screenshot shows choice box app. A selection furniture is made and save button is pressed. The save button call invokes a println method which prints out the object. Here the choice box printing out selection. The program puts a label, a choice box, and a button into an H box. An action is set on the save button, which print out the value. The simplest usage of choice box is to fill it with strings. This choice box in this article is built on a JavaFX class called pair. Pair is a general container for any key value pair and can be used in place of a domain or other special purpose object. Strings should only be used if they can be used without manipulation or decoded consistently. String converter. When using a complex object to back a choice box, a string converter is needed. This object serializes a string to and from a choice box. for this program, the only toString needs to be coded, which replaces the default toString of the pair. The pair object, both toString and fromString will need an implementation in order to compile. An empty object, empty pair, empty underscore pair is used to prevent null pointer exceptions. The return value from asset class dot get value can be accessed and compared consistently without adding special null handling logic. The choice box is used to select from a list of values. When a list of values is a complex type, provide the string formatter to serialize the list of object into something printable, if possible. If possible, use an empty object rather than null to support optional values. The complete code is here, and the code can be tested in a single .java file. Now here we are considering complete code here in VBox and HBox. In layouts, this is a completed JavaFX application subclass and main. The class VBox in package javafx.scene.layout in module javafx.graphics. VBox lays out its children in a single vertical column. If the VBox has a border and or padding set, then the contents will be laid out within those insects. The class HBox in package javafx.scene.layout in module javafx.graphics. HBox lays out its children in a single horizontal row. If the HBox has a border and or padding set, then the content will be laid out within those insects. The layout in VBox and HBox. Layout in JavaFX begins with selecting the right container controls. The two layouts controls are used most often VBox and HBox. VBox is a container that arranges its children in a vertical stack. HBox arranges its children in a horizontal row. The power of those two controls comes from wrapping them and setting a few key properties. Alignment, hgrow, and vgrow. This article will demonstrate these controls through a sample project. A mockup of the project shows a UI with the following: a row of top controls containing a refresh button and a sign out hyperlink, a table view that will grow to take up the extra vertical space, and a close button. The UI also features a separator which divides the top part of the screen with what may become a standard lower panel, save button, cancel button, etc. for the application. Here you can see the kind of mockup. VBox is the container, is the outermost container. VBox, this will be the parent provided to the scene. Simply putting UI controls in this VBox will allow the controls, most notably the table view, to stretch to fit the available horizontal space. The top controls, the refresh button and the sign out hyperlink are wrapped in HBox. Similarly, I wrap the bottom close button in the Xbox Hbox, allowing for additional buttons. This picture shows the mockup broken down by container. The parent's VBox is the outermost blue rectangle. The Hboxes are the inner rectangles, red and green. So this is a mockup broken down. Now we are considering alignment and edge grow. The refresh button is aligned to the left aligned to the left while hyperlink is aligned to the right. This is accomplished using two Hboxes. Top controls is a box. Top controls is a Hbox that contains the refresh button. And the also contains the an Hbox with sign out hyperlink. As the screen grows wider, the sign out hyperlink will be pulled to the right while the refresh button will retain its left alignment. The alignment is the property that tells a container where to position a control. Top controls set alignment to the bottom left. Top right control sets the alignment to the bottom right. The bottom makes sure that the baseline of the text refresh matches the baseline of the text sign out. In order to make sign out hyperlink move to the right when screen get wider, the priority dot always is needed. This is a cue to the JavaFX to widen top right controls. Otherwise, the top controls will keep keep this space, and top right controls will appear on the left. Sign out hyperlink still would be right aligned, but in a narrower container. Notice that set hgrow is a static method and neither invoke in on the top controls hbox nor in on itself. Top right controls. This is a facet of the JavaFX API that can be confusing because most of the API sets the properties via setters on objects. The close button the close button is wrapped in the hbox and positioned using the bottom right property. We grow since the outermost container is VBox. The child table view will expand to take the extra horizontal space when window is widened. However, vertically resizing the window will produce a gap at the bottom of the screen. The VBox does not automatically resize any of its children. As with the top right controls, hbox a grow indicator can be set. In the case of hbox, this was a horizontal resizing instruction set hgrow. For the table view container VBox, this will be set vgrow. There are few ways to space out UI controls. Now we are considering margin. This article uses the margin property on several of the containers to add white space around the controls. These are set individually rather than using spacing on the VBox, so that the separator will span the entire width. the insects used by table TBL customers omit any top spacing to keep the spacing even. JavaFX does not consolidate white spaces as in web design. If the top insect were set to 10.0D for the table view, the distance between top controls and the table view would be twice as wide as the distance between any other controls. Notice there are statics method like priority. This picture shows the application when run its initial 800 multiplied by 600 size. This image shows the application resized to a smaller heights and width here. Actually, this one is the resized image to a smaller width here. Select the right containers. The philosophy of JavaFX layout is the same as the philosophy of Swing. Select the right container for the task is at hand. This article presented the most versatile containers, VBox and HBox. By setting properties like alignment, hgrow and hgrow and vgrow, you can build incredibly complex layout through nesting. These are the containers I use the most and often are the only containers that I need. The complete code here. The code can be tested in a pair of .java files. There is a pocho for the customer object used by the table view. This is a completed JavaFX application, subclass and main. Now we are considering MVVM pattern in application structure. Here you can see the view, the employment request view dot class. The MVVM pattern, the model view, the model view model MVVM is a software architecture that separates UI controls, the view, from data access and business logic, the model. The separation helps large applications during the maintenance phase. With MVVM, view changes, especially those that are purely cosmetic, can be made without fear of introducing side effects. Changes to the model, usually less volatile than the view, can be applied more easily throughout the application because MVVM promotes reuse. In between the view and the model is the view model. The view model mediates between view and the model, yet contains no references to the view. This enables view model sharing, which is useful when two views show similar data. This article, here we present a simplified MVVM example. An employment request form submits several data elements to backend service. This screenshot shows the application with the same with the name, position, and annual salary data element set. This is the figure employment request form here. Entering data and after entering data and pressing save, the model object responds with a println. The program output here you can see. If the reset button is pressed after filling in the text fields, the form is restored to its original value, empty name and position and an annual salary of 0. The cancel button ends the application. The app, the main entry point, view UI controls, model function calls to the business logic and data access. View model contains screen stage and UI logic. Domain object, UI neutral transfer object. Converter, helper class for view model to model communication. This UML shows the structure of the employment request form. The view class is an employment request view which contains UI control object like the name, text, and like the text field. The view model class is employment request view model and contains JavaFX properties. The model class is the employment request model with a single method for persisting the form. The employment request converter is a helper class. Employment request is a POJO containing data fields. MVVM apps is the main entry point and JavaFX application subclass. UML class model of here UML class model of application view. In MVVM, the view class is responsible for UI controls and nothing else. Event handlers attached to UI controls delegate immediately to the view model. JavaFX data binding updates the UI with model changes. In the employment request form, 3 text fields gather input from the user. TF name, TF position, and TF annual salary. 3 buttons initiate operations on the application: btn save, btn cancel, btn reset. This is the beginning of the employment request view class here. Here the application MVVM app initiates app is connected to employment request via initiate, and employment request view is connected to employment request view model via binding and commands. Employment request model is connected to employment request converter, and employment request view model is connected to employment request model via provider persistent for. And here you can see domain model employment request. The view knows about view model and uses JavaFX binding to synchronize UI with the view model. This demo treats view model as a prototype object created when the view object is created. Alternatively, view model can be a singleton or provided by CDI. Each UI field is bound bidirectionally with the view model. As UI changes, say through entering a value of TF name, the corresponding field of the view model is updated. For more complicated expression for TF annual salary, field is needed to convert a string-based text field into double property. Here the employment request view class is continuing here. UI in this demo is built-in code. The following creative method handles the layout of the form and puts core controls such as tf name, and btn save in containers. Here the employment request view.class is continuing. The class ends with handlers for buttons. These handlers delegate their actions to the view model. Now we're considering here you can see the view model. The view model is a layer that interact with both view and the model. In this simple presentation, the value of such a layer is limited. One could just unpack the text field into model in the button handler. As the UI becomes more complex, it is useful to have a plainer, more business-oriented object to work with. While there is a one-to-one correspondence between view model and view model, that may always be the case. Handling many-to-many relationship is the key for view model. There may be many views that working with the same model element. Multiple models may contribute to a single view. In this view model look like domain object that will be presented later with one key difference. JavaFX binding employment request view model was bound to the employment request view UI controls and methods of employment request view model will have access to all of the information within the save method. No extra marshalling argument is needed. Employment request view model class you can see here. Both the converter and the model have been added to this view model as prototypes, meaning that they were created when the view model is created. The converter is a class that translates between view model view model and a domain object. In this app there is a single toEmployee request method that create an object from the view model fields. Here you can see employment request converter class. The model finally the model persists the information. This model this model example has a single method which verify that receives that it receive correct data for save operation. Employment request model class, here you can see it. This is the plain Java object used to transport data from model to UI. JavaFX provides developers uh, with a powerful toolkit to build applications. However, design is still needed for an effective program. MVVM is architecture patterns that separates the pure UI class UI classes called views from pure data classes called models. In the middle sits the view model, which relies heavily on the data binding or in JavaFX. Further work, sometimes view needs to know of a model change because MVVM dictates a one-way control flow, view to view model to model and not the reverse. The difference mechanism than data binding is needed to make view model aware of model changes. A publishing subscribing library can be used for this requirement, which would broker the view model, view model interaction. View model would receive a notification from the model, and the model would not require reference to the view model object. To read about MEVM and JavaFX, check out MEVM FX project in the documentation. The completed now we are considering stylable properties in best practices. The purpose of get class CSS metadata is to allow classes to easily include the CSS metadata of some anchor. The interface stylable property T in package javafx.css in module javafx.graphics. Stylable property allows a javafx.beans.property to be styled from CSS. The JavaFX property can be stylable properties in Java. A JavaFX property can be styled via CSS by using stylable property. This is useful when controls need properties that can be set via CSS. In order to use stylable property on a control, one need to create a new CSS metadata using stylable property. The CSS metadata is created for a control needs to be added to the list CSS metadata. Obtained from the controls ancestor. This new list is then returned from the get control CSS metadata. By conversion, the control class that have CSS metadata will implement the static method get class CSS metadata, and it is customary to have get control CSS metadata simply return get class CSS metadata. The purpose of get class CSS metadata is to allow subclasses to easily include CSS metadata of some ancestor. Creation of stylable property and CSS metadata needs a lot of a boilerplate code, and this can be reduced by using stylable property factory. Stylable property factory contains a method to create stylable property with corresponding CSS metadata. Here stylable property, typical JavaFX property implementation. CSS metadata, fetch CSS metadata from its ancestors. A new CSS metadata. Return all CSS metadata information. Stylable property, typical JavaFX property implementation. Stylable property factory, CSS metadata from stylable property factory. Return all CSS metadata information from stylable property factory. Now we are considering overview in introduction to FXML. FXML is a scriptable XML based markup language for constructing Java object graphs. It provides a convenient alternative to constructing such graphs in procedural code and is ideally suited to defining the user interface of a JavaFX application, since the hierarchical structure of an XML document closely parallels the structure of the JavaFX scene graph. Now we are considering instance declarations. Uh, in class instance elements, in elements, if an elements tag is considered an instance declaration, if the tag begins with the uppercase letter and this and the class is imported, here the following is a simple but complete example that creates instance of JavaFX.scene.control.label and sets its text property to hello world. The class label in package JavaFX scene.control in module JavaFX.controls. Label is a non-editable text control. A label is used for displaying text that is required to fit within a specific space, and thus may need to use an ellipsis and or truncation to size the string to fit. Labels also are useful in that they can have mnemonics which, if used, will send focus to the control listed as a target of the label for property. And if an element tag is considered an instance declaration, if the tag begins with the uppercase letter and the class is imported, or as in Java, it denotes a fully qualified, including the package name of a class. When fxml loader, also introduced later, encounters such an element, it creates an instance of that class. Importing a class is done using import processing instruction pi. For example, the following pi imports the JavaFX .scene.control package into the following pi imports the JavaFX.scene.control.label class into the current fxml documents namespace. If we put asterisk here, that will import all the classes from JavaFX.control package. Any class that adheres to Java Bean constructor and property naming conventions can be readily instantiated and configured using fxml. The following is a simple but complete example that creates an instance of JavaFX.scene.control.label and set its text property to hello world. Note that label's text property in this example is set using an XML attribute. Properties can also be set using nested property elements. Property elements are property attributes. Classes that don't conform to Bean conventions can also be constructed in fxml using an object called a builder. Now we are considering instance properties. In attributes, when the following markup is processed, x, y, width and height values will be converted to doubles, and the fill property will be converted to a color. The class rectangle in package javafx.scene.shape in module javafx.graphics The rectangle class defines a rectangle with a specified size and location. By default, the rectangle has sharp corners. Rounded corners can be specified by setting both the arc width and arc height properties to positive values greater than 0.0. Like property elements, attributes can also be used to configure properties of a class instance. For example, the following markup creates a button whose text reads click me. As with property elements, property attributes support type coercion. When the following markup is processed, x, y, width, height values will be converted to doubles, and the fill value will be converted to a color. Unlike property elements, which are applied as they are processed, property attributes are not applied until the closing tag of their respective element is reached. This is done primarily to facilitate the case where an attribute value depends on some information that won't be available until after the element's content has been completely processed. For example, the selected index of the tab pane control, which can't be set until all of the tabs have been added. Another key difference between property attributes and property elements in FXML is that attribute supports a number of resolution operators that extend their functionality. The following operators are supported: location resolution, resource resolution, and variable resolution. Under this topic, we can discuss these operators. Now we are considering scripting. The following example markup defines a function called handle button action that is called by the action handler attached to the button element. The JavaFX colon script tag allows a caller to import scripting code into or embed scripting within FXML file. Any JVM scripting language can be used, including JavaScript, Groovy, and Clojure, among others. Script code is often used to define event handlers directly in markup or in an associated source file, since the event handlers can often be written more concisely in more loosely typed scripting languages than they can be statically typed languages such as Java. Note the JavaScript script engine is disabled by default. If the JDK has a script engine, JavaScript script engine, it can be enabled using a system property javafx.allowjs equal true. Scripts are compiled by default when they are first loaded if the script engine implements javafx.script.compatible interface. If the compilation fails, the FXML loader will fall back to interpreted mode. Note, to run off the automatic compilation of script code, place the processing instruction compile false before the script element. To turn on the compilation of script code again, use processing instruction compile true or short compile. The compile processing instruction can be used repeatedly to turn compilation of the script code off and on. The following example markup define a function called handle button action that is called by the action handler attached to the button element. Clicking the button triggers event handler, which invokes the function producing output. Script code may also be defined in external files. Now we are considering controllers. As shown here, controllers are often used to implement event handlers for user interface element defined in the markup. While it can be convenient to write simple event handler in a script, either inline or defined in external files, it is often preferable to define more complex application logic in a compiled, strongly typed language such as Java. As discussed earlier, the fx controller attribute allows a caller to associate a controller class with the fxml document. A controller is compiled class that implements the code behind the object hierarchy defined by the document. The controllers are used to implement event handlers for user interface element defined in the markup. In many cases, it is sufficient to simply declare event handlers in this manner. However, when more control over the behavior of the controller and the elements it manages is required, the controller can define initialize method, which will be called once on implementing controller when the controller is when the content of the associated document have been completely loaded. Now we are considering @fxml. For example, the controllers from the previous examples could be rewritten as follows. The annotation interface fxml in package javafx.xml in module javafx.fxml. Annotation that tags a field or method as accessible to markup. Note that in the previous examples, the controller member fields and event handler methods were declared as public, so they can be set or invoked by the loader. In practice, this is not often an issue since the controller is generally only visible to the fxml loader that created. However, for developers who prefer more restricted visibility for controller fields and or handler methods, the JavaFX.fxml annotation can be used. This annotation marks a protected or private class member as accessible to fxml. If the class being annotated is in a named module, the module containing that class must open the containing package to at least JavaFX.fxml module. For example, the controllers from previous example could be rewritten as follows here. In the first version, the handle button action method is tagged with fxml at fxml to allow markup defined in the controller's document to invoke it. Now we are considering fxml loader. The type of the root element is assumed to be the subclass of JavaFX .scene.layout.pane, and the document is assumed to be assumed to define a controller type, define a controller of type myController. The class fxml loader in package javafx.fxml in module javafx.fxml. The class fxml loader loads an object hierarchy from an XML document for the fxml loader class is responsible for actually loading an fxml source file and returning the resulting object graph. For example, the following code loads an fxml file from the location on the class path relative to the loading class, and localizes it with the resource bundle name com.foo.example. The type of the root element is assumed to be a subclass of javafx.scene.layout.pane, and the document is assumed to define the controller of type myController. Note that the output of an fxml loader #load method operation is an instance hierarchy that reflects the actual named classes in the document, not org.w3c.dom nodes representing those classes. Internally, fxml loader uses the javafx.xml.stream API, also known as streaming API for XML or STAX, to load the fxml document. STAX is an extremely efficient event-based XML parsing API that is conceptually similar to its W3C predecessor, SAX. It allows an fxml document to be processed in a simple pass rather than loaded into loaded into an intermediate DOM structure and then post-processed. Now we are considering deploying an application as a module. For example, if com.foo.myController is in the foo, is in the foo.app module, the module -info.java might look like this. The fxml loader is used to load types in a named module. The application must ensure that all types are referenced in the fxml files, including the controller class and any custom node classes, are reflectively accessible to the javafx.fxml module. A type is reflectively accessible if the module opens the containing package to at least the javafx.fxml module. For example, if the com.foo.myController is in the foo.app module, the module info.java might look like this. Alternatively, a type is reflectively accessible if the module exports the containing package unconditionally. Now we are considering examples in introduction in contents in JavaFX CSS reference guide. Without any styles, this will display a plain black rectangle. If test.css contains the following, the rectangle will be red instead of black. To consider the following simple JavaFX application. So without any styles, this will display a plain black rectangle. If test.css contains the following, the rectangle will be in this test.css here. The rectangle will be red instead of black. Now we are considering a warning example. For example, this one. When a JavaFX CSS parser encounters a syntax error, warning message is emitted, which conveys as much information as available to help resolve the error. For example, this one. Warning, JavaFX CSS parser declaration expected % while passing -fx background color at $149. The cryptic $149 pertains to a location of the error. Format of the location is URL, line, and position. If the error is found while passing a file, the file URL will be given. If the error if the array is from an inline style, as in the example here, URL is given as a question mark. The line and the position give an offset into the file or string where the token begins. Please note that the line and position may not be accurate in releases prior to JavaFX 2.2. Applications needing to detect errors from the parser can add a listener to the errors property of the javafx.css.css parser. Now we are considering URI in types. Address is an hierarchical URI of the form scheme colon authority and then path, like here, for example here. if the address does not have scheme component, the address is considered to be the path component only. The leading / character indicates that the path is relative to the root of the class path. If the style appears in a style sheet and has no leading character, the path is relative to the base URI of the style sheet. If the style sheet appears in inline style, the path is relative to the root of the class path, regardless of whether or not there's a leading / leading /. Note that inline styles, for inline styles, the leading dot dash segments dot do resolve, since the path is always anchored at the root of the class path. As an example, the code snippet below creates a scene filled with fictional duke.png image located in an image directory. The same style would work equally as well from a style sheet. Now we are considering group in JavaFX.stage in stage. Style class root popup. Pop-up window does not have any properties that can be styled by CSS, but pop-up window does have its own scene. Scenes root gets the .root style class by default. If the scene is the root scene of the pop-up window, then the .popup style class is also added. This allows the root scene of the pop-up window to have distinct styled via the CSS rule .root .popup open curly brace, then declarations and close curly brace. Now we are considering available CSS pseudo classes in pseudo classes. So CSS pseudo class disabled applies when the disabled variable is true. Now we are considering accordion. In JavaFX.scene.control in controls, the style class accordion. The accordion control has all the properties and pseudo classes of control. Now we are considering area chart. In JavaFX.scene.charts. In charts, the style class chart series area line series I default color J, where I is the index of the series and the J is the series color index. The property is node. Here you can see hello app.class in overview in scene graph. One possible implementation that will produce a scene graph matching the figure above is as follows. The class scene in package JavaFX.scene in module JavaFX.graphics. The JavaFX scene class is the container for all content in scene graph. The background of the scene is filled as specified by the fill property. The result of running the code is seen in this figure. The important notes: the node can have maximum one parent. A node is the active attached to the currently visible scene, the scene graph. Can only be modified from the JavaFX application thread. Now we are considering translate in transformations. We will use the we can translate the box here by 100 pixels in x-axis and 200 pixels in y-axis. You can see the translated figure here. The public final void translate x double value defines the x coordinate of the translation that is added to this node's transform. Here y. This is in the class node. This method is in the class node and in the package JavaFX.scene, in the module JavaFX.scene, JavaFX.graphics. Now we are considering event handling. Let's create a custom event. The class event, which is in package JavaFX.event in module JavaFX.base. The base class for FX events. Each FX event has associated an event source. Event target and event type. The event source specifies for an event handler the object on which that handler has been registered and which send the event to it. The event target defines the path through which the event will travel when posted, and the event type provides additional classification to events of the same event class. An event notifies that something important has taken place. Events are typically the primitive of an event system, also known as event bus. Generally, an event system has the following three responsibilities: fire, trigger an event, notify listeners, notify listeners, interested parties about the event, and handle process uh, the event. An event notification mechanism is done by the JavaFX platform automatically. Hence, we will only consider how to fire event, listen for events, and how to handle them. Let's create a custom event here. Since event types are fixed, they are usually created within the same source file as the event. We can see that there are two specific types of events: logging succeeded and logging failed. We can listen for such specific types of events. Alternatively, we can handle any event if you put here .any. Finally, we are able to construct and fire our events. For example, login succeeded or login failed could be fired when a user attempt to log in to an app. Depending on the logging result, we can allow the user access the app or lock him out of the app. Whilst the same functionality can be achieved with a simple if statement, where there is one significant advantage of an event system. Event systems were designed to enable communication between various modules, subsystems in an application without tightly coupling them, such as a sound might be played by an audio system when the user log in, thus maintaining audio related code in its own module. However, we will not delve deeper into architectural styles here. Any other fields of importance, for example, data timestamp, handle event, Now we are considering timing. The following is the Java class of the demonstration program. It is important to understand the timing difference between creation of JavaFX UI controls and the display of the controls. When creating UI controls, either through direct API object creation or through FXML, you may be missing certain screen geometry values such as dimension of a window that is available later. At the instant when the screen is shown to the user, that showing event called onShown is the time at which a window has been allocated and final layout computations completed. To demonstrate this, consider the following program, which displays the screen dimensions while the UI controls are being created. um, and the screen dimensions when screen is shown. The following screenshot shows the running of the program when UI controls are being created. A new V box. A new scene. The primary stage dot set scene. There are no actual window height and width values available, as evident by the undefined n values. However, the values for the width and heights are available once window is shown. The program registers an event handler for the unshown event and prepares the same output. The following is the Java class of the demonstration program. Sometimes you will know the screen dimensions in advance, and you can use those values at any point in the JavaFX program. This includes before the unshown event. However, if your initialization sequence contains a logic that needs these values, you will need to work with the unshown event. A use case might be working with the last saved dimensions, so the dimensions based on program input. Before show method, I just see this to just set this to 480 multiplied by 320, right? All available now. We can consider this error, access restriction. The type application is not API restriction on required library rt.jar. This occurred in the environment of with JavaFX and Eclipse. As an error example 2, we can consider this error occurred in JavaFX 8. Error 3525 Java method getScene in class JavaFX.stage.window cannot be applied to given types. Required no arguments. Found JavaFX scene.scene reason actual and formal argument list differ in length. Now we are focusing on Quantum Toolkit. Quantum Toolkit ties Prism and Glass windowing toolkit together and makes them available to the JavaFX layer above them in the stack. It also manages the threading rules related to rendering versus event handling. As an example, we can consider Quantum Toolkit class. This class is in package com.sun.javafx.tk.quantum. As an example 2, we can consider JavaFX 8 command line option quantum.single threaded. This option is default to false. As an example, we can consider illegal state exception. Throw when shutdown hook already removed. This exception can be thrown from void dispose in class Quantum Toolkit. As an error example, we can consider this. This is occurred in as an illegal state exception while using com.sun.javafx.scene.web.debugger. Nested event loops are allowed only while handling system events at com.sun.javafx.tk.quantum.quantumtoolkit.enter nested event loop quantum toolkit.java, etc. Now we are focusing on Prism, JavaFX high performance graphics engine. Prism processes render jobs. It can run on both hardware and software renderers, including 3D. It is responsible for rasterization and rendering of JavaFX scenes. The following multiple render paths are possible based on the device being used: DirectX 9 on Windows XP and Windows Vista, DirectX 11 on Windows 7, OpenGL on Mac Linux embedded, Java 2D when hardware acceleration is not possible. The fully hardware accelerated path is used when possible, but when it is not available, the Java 2D render path is used because the Java 2D render path is already distributed in all of the Java runtime environments, JREs. This is particularly important when handling 3D scenes. However, performance is better when hardware render paths are used. As an example, we can consider package com.sun.prism. As an example too, we can consider this JavaFX 8 command line option. Prism.geforce GPU here. This force GPU this basically forces a GPU if GPU is PS3 capable, disable GPU qualification check. This is default to false. As an example, we can consider this non-invertible transform exception. This can be occurred from base transform, extract 3D, remainder base transform xform method in class base shader graphics. As an example, we can consider this java.land.nullPoint exception at com.sun.prism.impl.ps.base shader context.init lcd buffer at com.sun.prism.impl.ps.base shader context.validate lc d buffer, etc. Now we are focusing on Java 2D. Java 2D is an API for drawing two-dimensional graphics using the Java programming language. Every Java 2D drawing operation can ultimately be treated as filling a shape using a paint and compositing the result into the screen. Java 2D, when hardware acceleration is not possible, the fully hardware accelerated path is used when possible, but when it is not available, the Java 2D render path is used, because the Java 2D render path is already distributed in all of the Java runtime environments, JREs. This is particularly important when handling 3D scenes. However, performance is better when the hardware render path is used. Here you can see rendering pipeline. Primitive, you can see here primitives and here graphics 2D and output devices. In graphics through 2D, the rendering process can be broken into 4 phases that are controlled by the graphics 2D rendering attributes. The renderer can optimize many of these steps. Either by caching the results of the future calls, by collapsing multiple virtual steps into single operation, or by recognizing various attributes as common simple cases that can be eliminated by modifying other parts of the operation. The steps in the rendering process are: 1. Determine what to render. 2. Constrain the rendering operation to the current clip. The clip is specified by a shape in the usage space and is controlled by the program using various clip manipulation methods of graphics and graphics 2D. The user clips is transformed into a device space by the current transform and combined with device clip which is defined by the visibility of windows and device extents. The combination of user clip and the device clip define the composite clip, which determine the final clipping region. The user clip is not modified by rendering system to reflect the resulting composite clip. Determine what colors to render, and step 3. And step 4, apply the colors to the destination drawing surface using current composite attribute in the graphics 2D context. There are 3 types of rendering operations. Along with the details of each of their particular rendering processes are shape operations, text operations, and image operations. In shape operations, step 1, if the operation is a draw shape operation, then the create stroked shape method on the current stroke attribute in the graphics 2D context is used to construct a new shape object that contains the outline of the specified shape. Step 2, the shape is transformed from the user space to the device space using the current transform in the graphics 2D context. Step 3, outline of the shape is extracted using getPathIterator method of shape, which returns a path iterator object that iterates along the boundary of the shape. Step 4, if the graphics 2D object cannot handle the curved segment of the path iterator object returns, then it can call the alternative path iterator method of shape, alternate getPathIterator method of shape, which flatten the shape. Step 5, the current paint in the graphics 3D context is queried for the paint context, which specified the colors to render in the device space. Text operations. Step 1, the following steps are used to determine the set of glyphs required to render the indicated string. If the argument is a string, then the current font in the graphics 2D context is asked to convert the Unicode characters in the string into set of glyphs for presentation with whatever basic layout and shaping algorithms for font implements. If the argument is an attributed character iterator, the iterator is asked to convert itself to a text layout using embedded font attributes. The text layout implements more sophisticated glyphs layout algorithms that perform Unicode bidirectional layout adjustment automatically for multiple fonts of differing writing directions. If the argument is a glyph vector, then the glyph vector object already contains the appropriate font specific glyph codes with explicit coordinates for the position for each glyph. The current font is queried to obtain outlines for the indicated glyphs. These outlines are treated as shapes in user space relative to the position of each glyph that are determined by step 1. Step 3, the character outlines are filled as indicated in the shape operations. Step 4, the current paint is queried for a paint context which specifies the colors to render in the device space. Image operations. Step 1, a region of interest is defined by the bounding box of the source image. This bounding box is specified in image space, which is the image object's local coordinate system. Step 2, an affine transform is passed to draw image affine transform image observer method. The affine transform is used to transform the bounding box from image space to user space. If no affine transform is supplied, the bounding box is created as if it's already in the user space. Step 3, bounding box of the source image is transformed from user space into device space using the current transform. Note that the result of transforming bounding box does not necessarily result in a rectangular region in device space. Step 4, the image object determines what colors to render, sampled according to the source to the destination coordinate mapping specified by the current transform and optional image transform. The default rendering attributes. The default values for the graphics 2D rendering attributes are: for paint, it's the color of the component; font, the font of the component; stroke, a square pen with a line width of 1, no dashing, segment joints and square and end caps; transform, the default attribute, default value is the get default transform for the graphics configuration of the component. For composite, the default value is the alpha composite dot src underscore overrule. For clip, the default value is no rendering clip. The output is clipped to the component. Here you can see primitives, graphics 2D and output devices. Here you can see a shape is connected to stroke is connected to transform is connected to rasterizer, rendering hint is connected to rasterizer, and rasterizer is connected to clip is connected to paint, and paint is connected to composite is connected to screen and printer. In text, the text is connected to stroke is connected to font, and font is connected to transform is connected to rasterizer, rendering hint is connected to rasterizer is connected to clip is connected to paint is connected to composite, and composite is connected to screen and printer. In images, images are connected to transform is connected to rasterizer, rendering hint is connected to rasterizer is connected to clip is connected to composite composite is connected to screen and printer. Here you can see the graphics 2D class rendering context contains several attributes. Stroke, the pen attribute applied to the outline of the shape. These stroke attributes enable you to draw lines with any point size and dashing patterns, and apply end cap and join decorations to a line. The fill attribute is applied to a shape interior. This paint attributes enables you to fill shapes with solid colors, gradients and patterns. The composite attribute is used when rendered object overlap existing objects. The transform attribute is applied during rendering to convert rendered object from user space to device space coordinates. Optional translation, rotation, scaling and shearing transforms can also be applied to these attributes. The clip type restricts rendering to the area within the outline of the shape object used to define the clipping path. Any shape object that is used to define the clip. Font attribute is used to convert text string to glyphs. Rendering hints specify preferences in the trade-off between speed and quality. For example, you can specify whether anti-aliasing should be used if this feature is available. As an example, we can consider graphics 2D class. This graphics 2D class extends the graphics class to provide more sophisticated control over geometry, coordinate transformations, color management and text layout. This is the fundamental class for rendering two-dimensional shapes, text and images on the Java platform. This class is in package java.awt. As an example too, we can consider this JavaFX command line option. This configuration basically. Here prism.order implies which drivers to use. Here you can see J2D, Java 2D. As an exception example, we can consider this exception in canvas rendering when running Java 2D pipeline in the environment with Ubuntu 12.04 and Java version 1.7.0_4.0.4. Java.lang.illegal argument exception, alpha value out of range. at java.aw.alpha composite.init alpha init at java.awt.alpha composite.get instance alpha composite .java at java.awt.alpha composite.drive at com.sun.prism.j2d prism graphics set extra alpha etc. As an error example, we can consider this exception occurred in Canvas rendering when running the Java 2D pipeline in environment with Ubuntu 12.04 and Java version 1.7.0_04. Alpha value out of range and etc. And then com.sun.prism j2d prism graphics set extra alpha etc. Now we are focusing on OpenGL. OpenGL, Open Graphics Library, is a cross-language, cross-platform application programming interface API for rendering 2D and 3D vector graphics. The API is typically used to interact with the graphics processing unit GPU to achieve hardware accelerated rendering. In JavaFX OpenGL on Mac, Linux embedded. Here you can see OpenGL architecture. GPU is connected to display list and polynomial evaluator and per vertex operations and primitive assembly. Immediate mode is passed from CPU to per vertex operations and primitive assembly, and polynomial evaluator interacts with the display list and polynomial evaluator is connected to per vertex operations and primitive assembly. Per vertex operations and primitive assembly is connected to rasterization. Display list is connected to pixel operations. And pixel operations are connected to texture memory. Pixel operations are going through this path also, and pixel operations are connected to rasterization, and texture memory is connected to rasterization. Rasterization is connected to per fragment operations. Per fragment operations are connected to frame buffer. Frame buffer are connected to is connected to pixel operations. In a geometry pipeline, CPU is connected to vertex per vertex operations and primitive assembly through immediate mode, and And per vertex operations and primitive assembly is connected to rasterization. Rasterization is connected to per fragment operations. Per fragment operations are connected to frame buffer. Here you can see a diagram of the rendering pipeline. The blue boxes are programmable shader stages. The OpenGL rendering pipeline is initiated when you perform a rendering operation. Rendering operations require the presence of a properly defined vertex array object and a linked program object or program pipeline object, which provides the shaders for the programmable pipeline stages. Once initiated, the pipeline operates in the following order. 1. Vertex processing. Under that, each vertex retrieve from vertex arrays as defined by the VAO is acted upon the vertex shader. Each vertex in the stream is processed in turn into an output vertex. Then optional primitive tessellation stages and optional geometry shader primitive processing. The output is a sequence of primitives. Step 2, vertex post processing. The outputs of the last stage is adjusted or shipped to a different locations. Transform feedbacks happens here. Primitive assembly, primitive clipping, the perspective divide, and viewport transform to Windows space. Step 3, scan conversion and primitive parameter interpolation, which generate a number of fragments. Step 4, fragment shader processes each fragment. Each fragment generates a number of outputs. Pre-sample processing, including but not limited to scissor test, stencils test, depth test, blending, logical operations, right mask. Vertex specification. The process of vertex specification is where an application sets up an ordered list of vertices to send to the pipeline. These vertices define the boundaries of a primitive. Primitives are basic drawing shapes like triangles, lines, and points. Exactly how the list of vertices is interpreted as primitives is handled via a later stage. This part of the pipeline deals with the number of objects like vertex array objects and vertex buffer objects. Vertex array objects define what data each vertex has, while vertex buffer objects store the actual vertex data itself. A vertex data is a series of attributes. Each attribute is a small set of data that the next stage will do computations on. While a set of attributes do specify a vertex, there is nothing that says that part of a vertex attributes set needs to be a position or normal. Attributes data is entirely arbitrary. The only meaning assigned to any of it happens in the vertex processing stage. vertex rendering, once the vertex data is properly specified, then it is rendered as a primitive via a drawing command. Vertex processing, vertices fetch due to the prior vertex rendering stage begin. They are processing here. Vertex processing stages are almost all programmable operations. This allow user to code to customize the way vertices are processed. Each stage represent different kinds of shade operations. Many of these stages are optional. Vertex shader. Vertex shaders perform basic processing of each individual vertex. Vertex shaders receive the attribute inputs from the vertex rendering and converts each incoming vertex into a single outgoing vertex based on an attribute arbitrary user-defined program. Vertex shaders can have user-defined outputs, but there is also a special output that represent the final position of the vertex. If there is no subsequent vertex processing stages, vertex shaders are expected to fill this position with the clip space position of the vertex for rendering purposes. One limitation on vertex processing is that each input vertex must map to a specific vertex output vertex, and because vertex shader invocations cannot share state between them, the input attributes to output vertex data mapping is 1-to-1. That is, if you feed the exact same attribute to the same vertex shader in the same primitive, you will get the same output vertex data. This gives implementations the right to optimize vertex processing. If they can determine if they can detect that they are about to process a previously processed vertex, they can use previously processed data stored in a post transform cache. Thus, they do not have to run the vertex processing on that data again. Vertex shaders are not optional. Tessellation. Primitives can be tessellated using two shader stages and a fixed function tessellator between them. The tessellation control shader TCS stage comes first and determine the amount of tessellation to apply to a primitive, as well as ensuring connectivity between adjacent tessellated primitives. The tessellation evolution shader TES stage comes last, and it applies that interpolation or other operations used to compute user-defined data values for primitives generated by the fixed function tessellation process. Tessellation as a process is optional. Tessellation is considered active if a TES is active. TCS is optional, but TCS can only be used alongside a TES. Geometry shader. Geometry shaders are user-defined programs that process each incoming primitives, returning 0 or more output primitives. The input primitives for geometry shaders are the output primitives from a subset of primitive assembly process. If you send a triangle stripped as a primitive, what the geometry shader will see is a series of triangles. However, there are a number of input primitive types that are defined specifically for geometry shaders. These adjacency primitives give GCs a larger view of primitives They provide access to vertices of primitives adjacent to the current one. Output of a GS is 0 or more simple primitives, much like the output of primitives at assembly. The GS is able to remove primitives or tessellate them by outputting many primitives for a single input. GCS can also tinker with the vertex values themselves, either doing some of the work for vertex shader or just to interpolate the values when tessellating them. Geometry shaders can even convert primitives to a different types. Input points primitives can become triangles or lines can become points. Geometry shaders are optional. Vertex post-processing. After the shader based vertex processing, vertices undergo a number of fixed function processing steps. Transform feedback. The output of the geometry shader or primitive assembly are written to a series of buffer objects that have been set up for this purpose. This is called transform feedback mode. It allows a user to transform data via vertex or geometry shaders, then hold on to that data for use later. The data output into transform feedback buffer is the data from each primitive emitted by this step. Primitive assembly. Primitive assembly is the process of collecting a run of vertex data output from the prior stage and composing it into a sequence of primitives. The type of primitive the user rendered with determines how this process works. The output of this process is an ordered sequence of simple primitives, lines, points, or triangles. If the output is a triangle strip primitive containing 12 vertices, for example, the output of this process will be 10 triangles. If tessellation or geometry shaders are active, then the limited form of primitive assembly is executed before these vertex processing stages. This is used to feed those particular shader stages with individual primitives rather than a sequence of vertices. The rendering pipeline can also be absorbed at this stage. This allows the use of transform feedback operations without having to actually render something. Clipping. The primitives are then clipped. Clipped mean that primitives that lie on the boundary between the inside of viewing volume and outside are split into several primitives, such that the entire primitive lies in the volume. Also, the last vertex processing shader stage can specify user-defined clipping operations on a per vertex basis. The vertex positions are transformed from clip space to window space via a perspective divide and viewpoint transform. Face culling. Triangle primitives can be culled, that is discarded without rendering based on the triangle facing in the window space. This allows you to avoid rendering triangles facing away from the viewer. For closed surfaces, this triangle would naturally be covered up to by triangle facing the user, so there is never any need to render them. Face culling is a way to avoid rendering such primitives. rasterization, primitives that reach this stage are then rasterized in order in which they were given. Result of rasterizing a primitive is a sequence of fragments. Fragment is a set of state that is used to composite final data for a pixel or sample if multisampling is enabled in the output frame buffer. The stage for this fragment include its position on the screen space, the sample coverage if multisampling is enabled, and a list of arbitrary data that was output from previous vertex or geometry shader. This last set of data is computed by interpolating between the data values in the vertices for the fragment. The style of interpolation is defined by shader that outputted those values. Fragment processing. The data for each fragment from the rasterization stage is processed by a fragment shader. The output from the fragment shader is a list of colors for each of the color buffers being written to a depth value and a stencil value. Fragment shaders are not able to set the stenciled data for a fragment, but they do have control over the color and depth values. Fragment shaders are optional. If you render without a fragment shader, the depth and stencil values of the fragment get their usual values, but the value of all of the colors that a fragment could have are undefined. Rendering without a fragment shader is useful when rendering only a primitive default depth information to the depth buffer, such as when performing occlusion query test. Pre-sample operations. A fragment data output from the fragment processor is then passed through a sequence of steps. First step is a sequence of culling test. If the test is active, the fragment fails the test. The underlying pixels samples are not updated usually. Many of these tests are only active if the user activates them. The tests are pixel ownership test, fails if the fragment's pixel is not owned by the OpenGL, if another window is overlapping with the GL window. Always passes when using a frame buffer object. Failure means that pixel contains undefined values. Scissor test. When enabled, the test fails if the fragment pixel lies outside of the specified triangle of the screen. Stencil test. When enabled, the test fails if the stencil value provided by the test does not compare as the user specified against the stencil value from the underlying sample in the stencil buffer. Note that stencil value in the frame buffer can still be modified even if the stencil test fails, and even if the depth test fails. Depth test. When enabled, the test fails if the fragment's depth does not compare as the user specified against the depth value from the underlying sample in the depth buffer. Through these are specified to happen after the fragment shader, they can be made to happen before fragment shader under certain conditions. If they happen before fragment shader, Then any culling of the fragment will also prevent fragment shader from executing this saving performance. After this, color blending happens. For each fragment color value, there is a specific blending operations between it and the color already in the frame buffer at that location. Logical operations may also take place in lieu of blending, which perform bitwise operation between fragment colors and fragment frame buffer colors. Lastly, the fragment data is written to the frame buffer. Masking operations allow the user to prevent writes to certain values. Color, depth, and stencil write can be masked on and off. Individual color channels can be masked as well. Here you can see a vertex specification is connected to vertex shader. Vertex shader is connected to tessellation. Tessellation is connected to geometry shader. Geometry shader is connected to vertex post processing. Vertex post processing is connected to primitive assembly. Primitive assembly is connected to rasterization. Rasterization is connected to fragment shader. Fragment shader is connected to pre-sample operations. You can see programmable shade stages here: vertex shader, tessellation, geometry shader, and fragment shader. As an example, we can consider this code segment to make sure the JavaFX is using OpenGL Prism backend. So here ES2 is used. As example 2, we can consider this JavaFX 8 command line option. Prism order. This implies which driver to use. Here ES2, OpenGL ES 2.0. As an error example, we can consider this, and here you can see gog.opengl.gl gl drawable imply impl.unlock surface at gog.amp.opengl.gl context impl.release, etc. As an error example 2, we can consider this error occurred in environment with Raspberry Pi 2 with Ubuntu 14.04, libegl warning, DRI2 failed to authenticate, failed to create EGL context graphics device, initialization failed for ES2, error initializing quantum renderer, no suitable pipeline found java.lang.runtime exception. Now we are focusing on D3D. Direct 3D is a graphics application programming interface API for Microsoft Windows. Part of Direct 3D is used to render three-dimensional graphics in applications where performance is important, such as games. Direct 3D uses hardware acceleration if it is available on the graphics card, allowing for hardware acceleration of the entire 3D rendering pipeline or even only partial acceleration. Direct 3D exposes the advanced graphics capabilities of 3D graphics hardware, including Z buffering, W buffering, stencil buffering, spatial anti-aliasing, alpha blending, color blending, MIP mapping, texture blending, clipping, culling, atmospheric effects, perspective correct texture mapping, programmable HLSL shaders and effects. Integration with the other DirectX technologies enables Direct 3D to deliver such features as video mapping, hardware 3D rendering in 2D overlay planes, and even split, providing the use of 2D and 3D graphics in interactive media ties. In JavaFX, DirectX 9 on Windows XP and Windows Vista, DirectX 11 on Windows 7. Here you can see Direct 3D 11 programmable pipeline. Here you can see Direct 3D 11 programmable pipeline. The Direct 3D 11 programmable pipeline is designed for generating graphics for real-time gaming applications. This diagram shows the data flow from input to output through each of the programming stages. The graphics pipeline for Microsoft Direct 3D 11 supports the same stages as Direct 3D 10 graphics pipeline, with additional stages to support advanced features. You can use the Direct 3D 11 API to configure all of the stages that feature common shader cores. The rounded rectangular blocks are programmable by using HLSL programming language. As you will the input assembler stage, the Direct 3D 10 and higher API separates functional areas of the pipeline into stages. The first stage in the pipeline is the input assembler IA stage. The vertex shader stage. The vertex shader VS stage processes vertices from the input assembler, performing per vertex operations such as transformations, skinning, morphing, and per vertex lighting. Vertex shaders always operate on a single input vertex and produce a single output vertex. This vertex shader stage must always be active for the pipeline to execute. If no vertex modification or transformation is required, a pass-through vertex shader must be created and set to the pipeline. Tessellation stage. The Direct 3D 11 runtime supports 3 new stages that implement tessellation, which converts low detail subdivision surfaces into higher detail primitives on the GPU. Tessellation tiles or breaks up higher order surfaces into suitable structures for rendering. Geometry shader stage. The geometry shader GS stage runs application specified shader code with vertices as input and the ability to generate vertices on output. Stream output stage. The purpose of the stream output stage is to continuously output or stream vertex data from the geometry shader stage or vertex shader stage if the geometry shader stage is inactive to one or more buffers in memory. Rasterizer stage. The rasterization stage converts vector information composed of shapes or primitives into a raster image composed of pixels for the purpose of displaying real-time 3D graphics. The pixel shader stage. The pixel shader stage (PS) enables rich shading techniques such as per pixel lighting and post-processing. A pixel shader is a program that combines constant variables, texture data, interpolated per vertex values, and other data to produce per pixel outputs. The rasterizer stage invokes a pixel shader once for each pixel covered by a primitive. However, it is possible to specify a null shader to avoid running a shader. Output merger stage. The output merger OM stage generates the final rendered pixel color using a combination of pipeline stage. The pixel data generated by the pixel shaders, the contents of the render targets, and the contents of the depth stencil buffers. The OM stage is the final step for determining which pixels are visible with depth stencil testing and blending the final pixel colors. Here you can see input assembly stage is connected to vertex shader stage. Vertex shader stage is connected to hull shader stage. This hull shader stage is connected to tessellation stage or domain shader stage. Tessellation stage is connected to domain shader stage. Domain shader stage is connected to geometry shader stage, and geometry shader stage is connected to string output stage and rasterizer stage. Rasterizer stage is connected to pixel shader stage. Pixel shader stage is connected to output merger stage. Stream output stage is connected to memory resources. Memory resources, buffers, buffer, texture, constant buffer are connected to input assembly stage and vertex shader and hull shader stage and domain shader stage, geometry shader stage, and memory resources interacts with pixel shader stage and output merge stage, and as an example we can consider this package com.sun.prism.d3d. As an example 2 we can consider this JavaFX 8 command line option prism.order, which implies which driver to use. Here you can see D3D, direct 3D. As an exception example we can consider this one, illegal state exception, which can be occurred in void dispose in D3D pipeline, which is in the package com.sun.prism.d3d. As an error example we can consider this error message occurred in environment with JavaFX 11 or higher. Graphics device initialization failed for D3D SW. Error initializing quantum renderer, no suitable pipeline found, etc. Now we are focusing on glass windowing toolkit. The glass windowing toolkit is the lowest level in the JavaFX graphics stack. Its main responsibility is to provide native operating services such as managing the windows, timers, and surfaces. It serves as the platform-dependent layer that connects the JavaFX platform to the native operating system. As an example, we can consider this package com.sun.glass. As an example too, we can consider this code segment. Here the abstract class application in the JavaFX application class start and stop methods are called in the JavaFX application thread. The JavaFX application thread is part of the glass windowing toolkit in the com.sun.glass package hierarchy. JavaFX events are processed on the JavaFX application thread. All live scene manipulation must be performed in the JavaFX application thread. Nodes that are not attached to the live scene may be created and manipulated in other threads until they are attached to a live scene. Note the role the glass windowing toolkit plays in the JavaFX application is similar to that of AWT in Swing applications. It provides drawing surfaces and input events from the native platform. Unlike in AWT, where the EDT is different from the native platform's UI thread and communication has to occur between them. The native FX application, the JavaFX application thread in the glass windowing toolkit uses the native platform's UI thread directly. So the abstract class application related to these methods are in com.sun.glass package. Actually, this abstract class application is in package com.sun.glass package hierarchy. As an exception example, we can consider illegal state exception. If the current thread is not the event thread in static void event check static void check event thread method in class application. Now we are focusing on media engine. The media engine component has been designed with performance and stability in mind and provides consistent behavior across platforms. Here you can see classes in the JavaFX.scene.media package. The diagram shows boxes that represent the classes that reside in the JavaFX.scene.media package and the variables that each class includes. The boxes drawn from top to bottom and left to right are labeled media media player, media view, and media error event. Directional arrows connect the boxes. An arrow points from media box to the media player box. Another arrow points from media player box to media view box. And third arrow points up from the media error event to box to the media player box. The media class variables are duration, error, width, height, and on error. The media player class variables are status, volume, rate, autoplay, balance, mute, start time, stop time, total duration. The media view class variables are media player, X, Y, smooth, viewport, preserve ratio, fit height, and fit width. The JavaFX media concept is based on the following entities: media, the media resource containing information about the media, such as its source, resolution, and metadata. Media player, the key component providing the controls for playing media. Media view, a node object to support animation, translucency, and effects. Each element of the media functionality is available through the JavaFX API. This figure shows the classes that reside in the javafx.scene.media package. These classes are interdependent and are used in combination to create an embedded media player. The media player class provides all the attributes and functions needed to control media playback. You can either set autoplay mode, call the play function directly, or explicitly specify the number of times that the media should play. The volume variable and the balance variable can be used to adjust the volume level and right and left right settings respectively. Volume level range is from 0 to 1.0, the maximum value. The balance range is continuous from minus 1.0 on the far left, 0 at the center, and 1.0 at the right. The play, stop, and pause functions control media playback. Additionally, a bundle of functions handle a specific event when the player does one of the following: buffers data, reaches the end of media, stalls because it has not received data far enough to continue playing, encounters any of the errors defined in the media error event class. Media view class extends the node class and provide a view of the media being played by the media player. It is responsible mostly for effects and transformations. Its media player instance variable specifies the media player object by which the media is being played. Other Boolean attributes serve to apply the particular effect provided by the node class. For example, to enable the media player to be rotated. Here you can see media is connected to media player, media error event is connected to media player, and media player is connected to node. As an example, we can consider this package JavaFX.scene.media provides the set of classes for integrating audio and video into JavaFX applications. The primary use for this package is media playback. There are three principal classes in the media package: media, media player, and media view. As an example 2, we can consider this code segment. The class media player the media player class provides the control for playing media. It is used in combination with media and media view class. To display and control media playback. Media player does not contain any visual elements, so must be used with the media view class to view any video track which may be present. Media player is in the package javafx.scene.media. Here you can see a set cycle count method. Set the cycle count. Its effect will be constrained to 1 to integer.max value. Invoking this method will have no effect if media duration is duration.indefinite. Here the value is 50,000. Here the set rate method set the playback rate to the supplied value, here 4. Its effect will be clamped to the range 0.0 to 8.0. Invoking this method will have no effect if the media duration is duration.indefinite. The play method starts the playing media. If previously paused, then playback resumes where it was paused. If the playback is stopped, playback start from the start time. When playing actually start, the status will be set to media player.status.playing. Here the media view, a node that provides a view of media being played by media player. This following code snippet illustrate error handling with media. Errors using JavaFX media may be either synchronized or asynchronized. In general, synchronized errors will manifest themselves as an exception. And asynchronous errors will cause a JavaFX property to be set. In the latter case, either the error property may be observed directly, and on error callback registers, or possibly both. The main sources of synchronous errors are media, and media player, the asynchronous errors properties are media.error and media player.error, and the asynchronous error callbacks media dot on error and media player dot on error and media view dot on error. Some errors might be duplicated. For example, a media player will propagate an error that encounters to its associated media and media player to all its associated media views. As a consequence, it is possible to receive multiple notifications of the occurrence of a given error depending on which properties are monitored. Here you can see the section handle asynchronous error in media object. Here handle asynchronous error in media player object. And here handles asynchronous error in media view. Here handle asynchronous. Here handle synchronous error creating media player. And here handle exception in media player constructor. And here handle synchronous error in creating media. Handle exception in media constructor. Here you can see the code domain related to media engine is in green color. As an exception example, we can consider class media exception. A media exception describes a runtime error condition in a media player or media view. This class is in package javafx.scene.media. As an error example, we can consider this error occurred on line import JavaFX .scene .media. The error package JavaFX.scene.media does not exist. Now we are focusing on web engine. This web engine component is based on WebKit, which is an open source web browser engine that supports HTML5, CSS, JavaScript, DOM, and SVG. It enables developers to implement the following features in their Java applications: render HTML content from local or remote URL, support history and provide back and forward navigation, reload the content, apply effect to the web component, edit the HTML content, execute JavaScript commands, handle events. Here you can see a architecture of embedded browser and its relation to other JavaFX classes. Here you can see the scene graph here. In the JavaFX WebView is a mini browser, also called an embedded browser, that provides a web viewer and full browsing functionality to its API in JavaFX application. This browser is based on WebKit, that is an open source web browser engine that supports HTML5 and JavaScript, CSS, DOM rendering, and SVG graphics. The WebView class is an extension of the Node class. Here the web engine is a non-visual object capable of managing one web page at a time and provides basic web page functionality through its API. It supports user interaction such as navigation, links, and submitting HTML forms, although it does not interact with users directly. It loads web pages, creates their direct models, applies styles as necessary, and runs JavaScript on pages. It provides access to the document model of the current page and enables two-way communication between Java application and JavaScript code of the page. It wraps web page object which provide interaction with the native WebKit core. So here you can see scene, group, node, web view, and nodes are in scene graph, and scene is connected with connected to group, node, and web view. Group is connected to nodes. Web view interacts with the web engine. As an example, we can consider this class web engine. Web engine is a non-visual object capable of managing one web page at a time. It loads web pages, creates their document models, applies styles as necessary, and runs JavaScript on pages. It provides access to the document model of the current page and enables two-way communication between a Java application and JavaScript code of the page. This class is in the package JavaFX.scene.web. The following example changes the stage title. When loading completes successfully. The method final worker void get load worker get load worker returns worker object that can be used to track loading loading progress. Here the state property gets the read-only object property representing the current state. The web engine class provide two ways to load content into a web engine object from an arbitrary URL using the load java.land.string method. This method uses the java.net package for network access and protocol handling. From an in-memory string using the load content java.land.string and java.land.string and load content java.land.string methods. Loading always happens on a background thread. Methods that initiate loading return immediately after scheduling a background job. To track the progress and or cancel a job, use worker instance available from get load worker method. Here you can as an example 3 we can consider this code segment. Create a web view, web engine objects and load via remote URL. The class web view is a node that manages a web engine and displays its contents. The associated web engine is created automatically at construction time and cannot be changed afterwards. WebView handles mouse and some keyboard events and manages scrolling automatically, so there's no need to put it into a scroll pane. WebView is in the package JavaFX.scene.web. Here you can see a create a web view and get web engine via WebView and load URL. As an example, we can exception example we can consider runtime exception, which can be occurred in the method final string property user style sheet location property in class web engine. As an error example, we can consider this error occurred in the environment with semantic endpoint protection manager 14.3. The given URL is not valid, null. The given URL is not valid, could not initialize class javafx.scene.web.webengine. Now we are focusing on JDK API libraries and tools. JDK API libraries and tools. Here you can see conceptual diagram illustrating the components of Oracle's Java SC products. Here we are considering edition, Java Platform Standard Edition 8. Oracle has two products that implement Java Platform Standard edition, Java SC8, Java SC Development Kit, JDK, and Java SC Runtime Environment, JRE8. JDK 8 is a superset of JRE8, contains everything that is in JRE8 plus tools such as compilers and debuggers, necessary for developing applets and applications. JRE8 provides the libraries, the Java Virtual Machine, JVM and other components to run applets and application written in Java programming language. Note that the JRE includes components not required by the Java SC specification, including both standard and non-standard Java components. The Java conceptual diagram categorizes Java component technologies in levels. The technologies that are part of a lower level serves as the foundation for those that are part of higher level. Java language, tools and APIs, deployment and user interface toolkits, integration libraries, other base libraries, lang and util base libraries, Java Virtual Machine. JDK consists of all levels. JRE consists of the following level: deployment, user interface toolkit, integration libraries, other base libraries, and lang and util base libraries. Java SC API consists of following levels: deployment, no, sorry, not deployment is not included. User interface toolkits except JavaFX, integration libraries, other base libraries, and lang and util base libraries. Compact profiles consist of the following levels: integration libraries, other base libraries, and lang and util base libraries. JDK, Java SC Development Kit. JDK includes the JRE plus command line development tools such as compilers and debuggers that are necessary or useful for developing applets and applications. JRE, JavaSC Runtime Environment. The JRE provides the libraries, Java Virtual Machine, and other components necessary for you to run applets, an application written in Java programming language. This runtime environment can be redistributed with applications to make them freestanding. JavaSC API, Java Platform Standard 8 API specification. Compact profiles. Compact profiles introduced in JDK 8 enable reduced memory footprints for applications that do not require the entire Java platform. The JavaC compiler has a dash profile options, which allows the application to be compiled using one of the supported profiles. Java language. A Java programming language is a general purpose concurrent, strongly typed, class-based, object-oriented language. It is normally compiled to the bytecode instruction set and binary format defined in the Java Virtual Machine specification. Java JDK tools and utilities. Java launches a Java application. The Java command starts a Java application. It does this by starting a Java runtime environment, JRE, loading the specified class, and calling the class's main method. The method must be declared public and static. It must not return any value, and it must accept a string array as a parameter. JavaC, the Java programming language compiler, JavaC. The Java programming language compiler, JavaC, reads source files written in the Java programming language and compiles them into bytecode class files. Optionally, the compiler can also process annotations found in source and class files using pluggable annotation processing API. The compiler is a command line tool but can also be invoked using Java Compiler API. The compiler accepts source code defined by the Java language specification, JLS, and produces class files defined by the Java Virtual Machine specification, JVMS. Java Doc. The Java Doc is a tool that passes the declarations and documentation commands in a set of source files and produces a set of HTML pages describing the classes, interfaces, constructors, methods, and fields. You can use a Java doclet to customize Java doc output. A doclet is a program written with the doclet API that specifies the content and format of the output to be generated by the tool. You can write a doclet to generate any kind of text file output such as HTML, HGML, XML, RTF, and MIF. Oracle provides a standard doclet for generating HTML format API documentation. Doclets can also be used to perform special tasks not related to producing API documentation. Java Archive, Java Files. Java Archive is a platform independent file format that aggregates many files into one. Multiple Java applets and their request components, .class files, images, and sounds can be bundled in a Java file and subsequently downloaded to a browser in a single HTTP transaction, greatly improving the download speed. The Java format also supports compression, which reduces the file size, further improving the download time. In addition to applets, author can digitally sign individual entries in a jar file to authenticate their origin. It is fully extensible. Java P deassembles one or more class files. Java P command deassembles one or more class files. The output depends on the options used. When no options are used, then the Java P command prints the package, protected and public fields and methods of the classes passed to it. The Java P command prints its output to std out. JDEPS Java Class Dependency Analyzer. The JDEPS command shows the package level or class level dependencies of a class files. The input class can be a path name to a .class file, a directory, or a jar file, or it can be fully qualified class name to analyze all class files. The options determine the output. By default, JDEPS outputs the dependencies to the system out. It can generate the dependencies in .dot language. Scripting Java Web Services tools. Schema generator for Java architecture for XML binding. WSGen tool to generate JAX WS portable artifacts. WS import tool to generate JAX WS portable artifacts. XJC binding compiler for Java architecture for XML binding. Security. These security tools help you to set security policies on your system and create applications that can work within scope of security policies set at remote sites. Key tool, manage keystrokes and certificates. Jar signer, generate and verify jar signatures. Policy tool, GUI tool for managing policy files. Monitoring tools. You can use the following tools to monitor JVM performance statistics. The tools described in these sections are unsupported and experimental and should be used with that in mind. They may not be available in future JDK versions. These tools are supported on all platforms except Windows 98 and Windows ME. JPS experimental JVM process status tool. List instrumental hotspot Java virtual machines on target system. JStat experimental JVM statistics monitoring tool attaches to an instrumental hotspot Java virtual machine and collects and logs performance statistics as specified by the command line options. JStatD experimental JVM JStat daemon launches RMI server application that monitors for the creation and termination of instrumental hotspot Java virtual machines and provide an interface to allow remote monitoring tools to attach to a Java virtual machine running on local system. JConsole, a JMX compliant graphical tool for monitoring a Java virtual machine. It can monitor both local and remote JVMs. It can also monitor and manage an application. Java Visual VM. Java Visual VM is a tool that provides a visual interface for viewing detailed information about Java applications while they are running on a Java virtual machine JVM, and for the troubleshooting and profiling these applications. Various optional tools including Java VM are provided with the Java Development Kit JDK for retrieving different types of data about running JVM software instances. For example, most of the previously standalone tools, JConsole, JStat, JInfo, JStack, and JMap are part of Java Visual VM. Java Visual VM federates these tools to obtain data from the JVM software, then reorganizes and presents the information graphically to enable you to view different data about multiple Java applications uniformly, whether they are running locally or remote machines. Furthermore, developers can extend the Java Visual VM to add new functionality by creating and posting plugins to the tool's built-in update center. JMC, JDK Mission Control. JDK Mission Control, JMC, is an advanced set of tools for managing, monitoring, profiling, and troubleshooting Java applications. JMC enables efficient and detailed data analysis for areas such as code performance, memory, and latency without introducing the performance overhead normally associated with profiling and monitoring tools. JFR, Java Flight Recorder, is a tool for collecting, diagnosis, and profiling data about a running Java application. It is integrated into Java Virtual Machine and causes almost no performance overhead, so it can be used even in heavily loaded production environment. The default settings are used both internal testing and customer feedback. Internal testing and customer feedback indicate that performance impact is less than 1%. For some applications, it can be significantly lower. However, for short running applications, which are not a kind of applications running in the production environments, relative startup and warm-up times can be larger, which might impact the performance by more than 1%. JFR collects data about the JVM as well as the Java application running on it. JPDA, Java Platform Debugger Architecture. The Java Platform Debugger Architecture, JPDA, consists of three interfaces designed for use by debugger in development environment for desktop systems. The Java Virtual Machine Tools interface, JVM TI, defines the services a VM must provide for debugging. Java Debug Via Protocol, JDWP, defines that the format of information and requests transferred between processing being debugged and debugger frontend, which implements Java Debug Interface, JDI. Java Debug Interface defines information and request at the code level. JVM TI, Java Virtual Machine Tool Interface. The JVM Tool Interface, JVM TI, is a native programming interface for use by tools. It provides both a way to inspect an state and to control execution of applications running in the Java Virtual Machine JVM. JVM TI supports full breadth of tools that need access to JVM state, including but not limited to profiling, debugging, monitoring, thread analysis, and coverage analysis tools. Java IDL and RMI IOP tools. These tools are used when creating applications that use OMG standard IDL and COBA IIOP. TNAM ESERV provide access to the naming service. IJ generates .java files that map an OMG IDL interface and enable an application written in the Java programming language to use COBA functionality. ORBD provides support for clients to transparently locate and invoke persistent objects on servers in the COBA environment. Server tool provides ease of use interface for application programmers to register, unregister, start up and shut down a server. Remote method invocation, RMI tools. These tools help to create applications that interact over the web or other networks. RMIC generates stubs and skeleton for remote object. RMI registry, remote object registry service. RMID, RMI activation system daemon. Serial VER returns class serial version UID. JavaDB 10.11 document. JavaDB is a relational database management system that is based on Java programming language. Java deployment tools, utilities for use in conjunction with deployment of Java applications and applets on the web. Java packager perform tasks related to packaging and signing Java and JavaFX applications. Pack 200 transform a Java file into a compressed Pack 200 file using Java gzip compressor. Compressed packed files are highly compressed Java, which can be directly deployed, saving bandwidth and reducing download time. Unpack 200 transform a packed file produced by Pack 200 into Java file. Internationalization tools. This tool helps to create localizable applications. Native to ASCII, convert text to Unicode Latin 1. Web services tools. Schema generator for Java architecture for XML binding. VS Gen tools to generate Java WS portable artifacts. Sorry, it's WS Gen. WS import tool to generate WS portable artifacts. XJC binding compiler for Java architecture for XML binding. Here in scripting, following tools can be used to run scripts that interact with the Java platform. JJS runs the --horn command line script shell. JRun script experimental script shell for Java runs a script. This tool is unsupported and experimental in nature and should be used within that in mind. it might not be available in future JDK versions. Uh, Troubleshooting tools. The following tools can be used for specified troubleshooting tasks. The tools described in this section are unsupported and experimental in nature and should be used with that in mind. They may not be available in future JDK versions. Some of these tools are not currently available on Windows. JInfo, experimental configuration info for Java, prints configuration information for a given process or core file or a remote debug server. JHat, experimental heap dump browser, start a web server on the heap dump file, for example produced by jmapdump, allowing the heap to be browsed. JMap, experimental memory map for Java, prints shared object memory maps or heap memory details of a given process, core file or remote debug server. JSA debug D, experimental serviceability agent debug daemon for Java, attaches a process or core file that acts as a debug server. JStack, experimental stack trace for Java, prints a stack trace of threads for given process or core file or remote debug server. Deployment. Have an application ready to publish. Follow these steps for basic deployment. Step 1, decide how you want users to access and run your application. Step 2, create the application package. Step 3, set up the web page, or if your application is embedded in a web page or is launched from the browser. Step 4, copy the package to the location from which you want users to access it. Java Web Start. Java Web Start is an application deployment technology that gives you the power to launch full-featured applications with a single click from your web browser. You can now download and launch applications such as complete spreadsheet program or internet chat client without going through complicated installation procedures. Java applet and Java plugin. Java plugin technology, hereafter the Java plugin, which is included in the Java runtime environment JRE, enables Java applets to run in web browsers on desktop. Java plugin provides powerful capabilities to applets in the web browser while improving overall reliability and functionality of applets in a backward compatible manner. User interface libraries. Swing implements a set of components for building graphical user interfaces, GUIs, and adding rich graphics functionality and interactivity to Java applications. Swing components are implemented entirely in the Java programming language. The pluggable look and feel lets you to create GUIs that can either look the same across platforms or can assume the look and feel of the current OS platform, such as Microsoft Windows, Solaris, or Linux. Java 2D graphics and imaging. Java 2D API is a set of classes for advanced 2D graphics and imaging. It encompasses line art, text, and images in a single comprehensive model. The API provides extensive support for image composing and alpha channel images, a set of classes to provide accurate color space definition and conversion, and a rich set of display-oriented imaging operations. These classes are provided as additions to the java.awt and java.awt.image packages. Abstract Window Toolkit AWT. The Abstract Window Toolkit supports graphical user interface GUI programming. AWT features include a set of native user interface components, a robust event handling model, graphics and imaging tools, including shape, color, and font classes, layout managers for flexible window layouts that do not depend on a particular window size or screen resolution, data transfer classes for cut and paste through the native platform clipboard. Accessibility, Java accessibility guide. The enabling accessibility. If you have a Java application that was designed for use the Microsoft Windows accessive technology and program and Java Accessibility API, JAAPI program. With the Java Accessibility API, developers can easily create Java applications that are accessible to persons with disabilities. Drag and drop. Drag and drops enables data transfer across Java programming language and native applications, between Java programming language applications, and within single Java programming language applications. The Java Input Method Framework (IMF) technology. The input method framework enables the collaboration between text editing components and input method for entering text. Input methods are software components that let the user enter text in ways other than simple typing on a keyboard. They are commonly used to enter Japanese, Chinese, or Korean languages using thousands of different characters on keyboards with far fewer keys. However, the framework also support input methods for other languages and the use entirely of different input mechanisms such as handwriting or speech recognition. Java Image I/O technology. Java Image I/O API, developed through JSR 015, provides a pluggable architecture for working with images stored in files and accessed across the network. It offers substantially more flexibility and power than the previous APIs for loading and saving images. The API provides a framework for the addition of format-specific plugins. Plugins for several common formats are included with Java Image I/O, but third parties can use this API to create their own plugins to handle special formats. Java Print Service. The Java Print Service API allows printing on all Java platforms, including requiring a small footprint such as a Java ME profile, but also support the java.awt.print.print job API. The Java Print Service API includes an extensible print attribute set based on the standard attributes specified in the internal printing protocol IPP 1.1 from the IETF. With the attributes, client and server applications can discover and select printers that have the capabilities specified by attributes. In addition to the included stream print service, which allows applications to transcode data to a different formats. Third parties can dynamically install their own print services through the service provider interface. Java sound technology. The Java platform includes powerful API for capturing, processing, and playing back audio and MIDI, musical instrument digital interface data. This API is supported by an efficient sound engine which guarantees high quality audio mixing and MIDI synthesis capabilities for the platform. Integration libraries. IDL Java IDL technology adds COBA common object request broker architecture capability to the Java platform, providing standard-based interoperability and connectivity. Java IDL enables distributed web-enabled Java application to transparently invoke operations on remote network services using the industry standard IDL, Object Management Group Interface Definition Language, and IIOP Internet Inter-ORB protocol defined by the Object Management Group. Runtime components includes Java ORB for distributed computing using IIOP communication. Java JDBC API. The Java database connectivity JDBC API provides universal data access from Java programming language. Using the JDBC API, you can access virtually any data source from relational databases to spreadsheet and FATS files. JDBC technology also provides a common base on which tools and alternative interfaces can be built. Java Naming and Directory Interface JNDI. The Java Naming and Directory Interface JNDI provides naming and directory functionality to applications written in Java programming language. It is designed to be independent of any specific naming or directory service implementation. Thus, a variety of services, new, emerging, and already deployed ones, can be accessed in a common way. RMI Java Remote Method Invocation API Java RMI. Java Remote Method Invocation Java RMI enables the programmer to create distributed Java technology based applications in which the methods of remote Java objects can be invoked from other Java virtual machines, possibly on different hosts. RMI uses object serialization to marshal and unmarshal parameters and does not truncate types, supporting true object-oriented polymorphism. Java RMI over IIOP. Java Remote Method Invocation over Internet Inter-ORB Protocol Technology RMI IIOP is a part of Java Platform Standard Edition Java SC. RMI programming model enables the programming of COBA servers and applications via RMI API. You can choose to work completely within the Java programming language using Java Remote Method Protocol JRMP as the transport, or work with other COBA compliant programming languages using Internet or Inter-ORB Protocol IIOP. Scripting for Java platform. Many implementations of scripting and dynamically typed languages generate Java bytecode so that programs can be run on the Java platform, just as are actual Java programs. Implementing a language in this way, or as a Java interpreter class for scripting language, provides all the advantages of Java platform. Scripting implementations can take advantage of the Java platform's binary portability, security, and high performance bytecode execution. uh, other base libraries. uh, Java Beans Component API. The Java Beans Component API extends the Java platform write once, run anywhere capability to reusable components development. In fact, the Java Beans architecture takes interoperability a major step forward. Your code can run on every OS and also within any application environment. A developer can create component based on the Java Beans architecture. Beans secure a future in emerging network software market without losing customers that use proprietary platforms, because Beans interoperate with ActiveX, OpenDoc, and Live Connect. Long-term persistence of for Beans, Java Beans enables you to read and write Beans as a textual representation of its property values. Security. Java security technology include a large set of APIs, tools, and implementations of commonly used security algorithms, mechanisms, and protocols. Java security APIs span a wide range of areas, including cryptography, public key infrastructure, secure communication, authentication, and access control. Java security technology provides the developer with a comprehensive security framework for writing applications, and also provide the user or administrator with a set of tools to securely manage applications. uh, Java object serialization. Object serialization supports the encoding of objects and objects reachable from them into a stream of bytes. Serialization also supports the complementary reconstruction of the object graph from a stream. Serialization is used for lightweight persistence for communication via sockets or Java remote method invocation, Java RMI. The default encoding of objects protect private and transit data and supports evolution of classes. A class may implement its own external encoding and is then solely responsible for the external format. Extension mechanisms for support of optional packages. This feature has been deprecated and will be removed in future release. Optional packages are packages of classes and any associated native code that application developer can use to extend the functionality of the core platform. The extension mechanism allows the Java Virtual Machine VM to use classes of optional extension in much the same way as the VM uses classes in the Java platform. The extension mechanism also provides a way to wait for needed optional packages to be retrieved from specified URLs when they are not already installed in the JDK or JRE. Java Management Extensions, JMX. The Java Management Extensions, JMX API is a standard API for management and monitoring of resources such as applications, devices, services, and Java Virtual Machine. The JMX technology was originally developed through the Java Community Process (JCP) as Java Specification Request (JSR3), Java Management Extensions, and JSR 160 JMX Remote API. XML in JavaSC. XML extensible markup language is a flexible way to create common platform formats to and share both the format and the data on the World Wide Web, intranets, and elsewhere. XML can be used uh, by any individual or group of individuals or companies that wants to share information in a consistent way. uh, Networking, Java networking, uh, Java.NET package, JavaX.NET package, JavaX.NET SSL package, com.sun.net.http server package, com.sun.net.http server.spi package, jdk.net package. Java endorse standards override mechanism. This feature will be is deprecated and will be removed in future release. For time to time, it is necessary to update the Java platform in order to incorporate newer versions of standard that are created outside of the Java community process endorse standard, and or in order to update the version of a technology included in the platform correspond to a later standalone version of the technology. The endorse standards override mechanism provides a means whereby the later versions of classes and interfaces that implement endorse standard or standalone technologies may be incorporated into the Java platform. Java Native Interface. Java Native Interface JNI is a standard programming interface for writing Java native methods and embedding Java virtual machine into native applications. The primary goal is binary capability of native method libraries across all Java virtual machine implementations on a given platform. Java date and time packages. The datetime APIs introduced in JDK 8 are a set of packages that model the most important aspect of Java of date and time. The core classes in the Java.time package use the calendar system defined in ISO 8601 based on the Gregorian calendar system as a default calendar. Other non-ISO calendar systems can be represented using java.time.chrono package, and several predefined chronologies such as Hiraj and Thai Buddhist are provided. Java IO, NIO, and NIO.2. Java IO support is included in the Java IO and Java NIO packages. Together, these packages include following features: input and output through data streams, serialization and file system, charsets, decoders, encoders for translating between bytes and Unicode characters, access to file attributes and file systems, APIs for binding scalable servers using asynchronous or multiplex non-blocking I/O. Java internationalization support. Internationalization is the process of designing an application so that it can be adapted to various languages and regions without engineering changes. Sometimes the term internationalization is abbreviated as I18N because there are 18 letters between the first I and the last N. Lang and util packages provides the fundamental object and classes, wrapper classes for primitive types, and a basic math class, and more. Core Java Math. The math functionality includes the floating point libraries java.lang.math and java.lang.strictmath, and arbitrary position math java.math package. The collections framework. The collections framework is a unified architecture for representing and manipulating collections, enabling them to be manipulated independently of details of their representation. It reduces programming effort while increasing performance. It enables interoperability among unrelated APIs, reduces effort in designing and learning new APIs, and fosters software reuse. The framework is based on more than a dozen collection interfaces. It includes implementation of these interfaces and algorithms to manipulate them. Package java.lang.ref provide reference object classes which support a limited degree of interaction with garbage collector. Regular expressions. Package java.util.regex classes for matching character sequences against patterns specified by regular expressions. Java logging technology. The Java logging API is introduced in package java.util.logging facilitate software servicing and maintenance at customer sites by producing log reports suitable for analysis by the end users, system administrators, field service engineers, and software development teams. The logging APIs capture information such as security failures, configuration errors, performance bottlenecks, and or bugs in the applications or platforms. Monitoring and management for Java platform. The Java Platform Standard Edition provides comprehensive monitoring and management support for the platform. Instrumentation. Java.lang.instrument package. Java.lang.instrument package provides a Java programming language API for tools to instrument Java programming language applications, for example, to monitor them or collect performance information. Tools use java.lang.instrument to modify the class file that define the class, generally by inserting into the bytecode of methods additional bytecode which perform instrumentation. Java concurrency utilities. The concurrency utilities package provide powerful extensible framework of high performance thread utilities such as thread pools and blocking queues. This package frees the programmer from the need to craft these utilities by hand in much same manner the collections framework did for data structures. Additionally, these packages provide low-level primitives for advanced concurrent programming. The Java Reflection API. The reflection enables Java code to discover information about the fields, methods, and constructors of load classes and use reflected fields, methods, and constructor to operate on their underlying counterparts within security restrictions. The API accommodates applications that need to access to either the public members of the target object based on its runtime class or the members declared by a given class. It also allows programmers to suppress default reflective access control. The package version identification versioning. The versioning feature enables package level version control so that applications and applets can identify the runtime version, the version of a specific Java runtime environment's VM and class package. Core Java Preferences API. Applications require preference and configuration data to adapt to the needs of different users and environment. The java.util.prefs package provides a way for applications to store and retrieve the user and system preference and configuration data. The data is stored persistently in an implementation dependent backing store. There are two separate trees of preference nodes, one for user preference and one for system preference. Java Archive, Java files. The Java Archive is a platform independent file format that aggregate many files into one, multiple Java applets, and their request component. Class files, images, and sound can be bundled in a Java file and subsequently loaded to a browser in a single HTTP transaction, greatly improving the download speed. The Java format also supports compression, which reduces the file size, further improving the download time. In addition, the applet author can digitally sign individual entries in a Java file to authenticate their origin. It is fully extensible. The package java.util.zip provide classes for reading and writing standard zip and gzip file format. Also include classes for compressing and decompressing data using the deflate compression algorithm, which is used by the zip and gzip file format. Additionally, there are utility classes for computing the crc32 and edler32 checksums of arbitrary input streams. Java virtual machine technology. The JDK provide one or more implementation of Java virtual machine. On platform typically use the client applications. The JDK comes with the VM implementation called Java Hotpots client VM. The client VM is tuned for reducing the startup time and memory footprint. It can be invoked by the client command line option when launching the application. On all platforms, JDK comes with an implementation of a Java virtual machine called Java Hotpots Server VM. The server VM is designed for maximum program execution speed, so it can be invoked by using the -server command line option when launching the application. And you can also see JavaFX here. JavaFX is a set of graphics and media packages that enable developers to define, create, and test and debug and deploy rich client applications that operate consistently across diverse platforms. Here you can see JDK and JRE and compact profiles and Java SE API. In Java languages, you can see Java language, tools and API, Java, Java C, Java Doc, Java P, JD, EPS, scripting, security monitoring, JConsole, Java VM, JMC, JFR, JDPA, JPDA, JVM, TI, IDL, RMI, Java DB, deployment, internationalization, web services, troubleshooting, and deployment, Java Web Start, Applet, Java plugin, and JavaFX, user interface toolkits, Swing, Java 2D, AWT, accessibility, drag and drop, input methods, image IO, print service, and sound. Integration libraries, IDL, JDBC, JNDI, RMI, RMI IOP, and scripting. Other base libraries are Beans, security, serialization, extension mechanism, JMX, XML, JAXP, networking, override mechanism, JNI, date and time, input output, internationalization. Java Lang and utils, Java Lang and util based libraries, math collections, reference REF objects, regular expressions, logging, management, instrumentation, concurrency utilities, reflection, versioning, preferences, API, Java ship, Java virtual machine, Java hotspot client, and server VM. Here you can see a scene builder could also implement the view in FXML and scene builder. In this example, the UI is built in in code. Scene builder is a design-oriented alternative that can be more productive. To convert this example to FXML, the product of the scene builder, you would build the UI in the tool and annotate the field and methods of the employment request class with at FXML, for example. See the following screenshot for how the demo look like in scene builder here. This is informational only and not part of the working demo. Notice that the right half of the UML diagram in MEVM, it's not shown here, could be changed by switching the view implementation from code to scene builder. A sign of a good design is when alternative presentations can be supported easily. As an example, we can consider java.lang package. Provides classes that are fundamental to the design of the Java programming language. Java, as example 2, we can consider Java C, the programming language compiler Java C. The programming language compiler Java C reads source files written in the Java programming language and compiles them into bytecode class files. Optionally, the Java compiler can also process annotations found in source and class files using pluggable annotation processing API. The compiler is a command line tool but can also be invoked using Java compile API. The compiler accepts source code defined by the Java language specification JLS and produces class files defined by Java virtual machine specification JVMS. Now we are considering FXML and scene builder in MVVM pattern in application structure. Scene builder is a design-oriented alternative that can be more productive. Exception example, class exception. The class exception and its subclasses are a form of throwable that indicates condition that a reasonable application might want to catch. This is in package java.lang. Now we are focusing on Java virtual machine. A Java virtual machine, JVM, is a virtual machine that enables a computer to run Java programs as well as programs written in other languages that are also compiled to Java bytecode. The JVM is detailed by a specification that formally describes what is required in a JVM implementation. Having a specification ensures interoperability of Java programs across different implementation, so that program authors using the Java Development Kit JDK need not worry about idiosyncrasies for the underlying hardware platform. Here you can see the JVM architecture diagram. A virtual machine is a software implementation of physical machine. Java was developed with the concept of WORA, write once, run anywhere, which runs on a VM. The compiler compiles the Java files into a java.class file. Then that .class file is input into JVM, which loads and executes the class files. As shown in this diagram, JVM is divided into three main subsystems: class loader subsystem, runtime data area, and execution engine. Class loader subsystem. The Java's dynamic class loading functionality is handled by the class loader subsystem. It loads links and initializes the class file when it refers to a class for the first time at runtime, not compile time. Loading classes will be loaded by this component. Bootstrap class loader extension, class loader and application class loader are the three class loaders that will help in achieving it. Bootstrap class loader, responsible for loading classes from the Bootstrap class path. Nothing but rt.jar highest priority will be given to this loader. Extension class loader, responsible for loading classes which are inside the ext folder jre /lib. Application class loader, responsible for loading application level class path mention, environment variables, etc. These class loaders will follow delegation hierarchy algorithm while loading the class files. Linking, verify, bytecode verify will verify whether the generated bytecode is proper or not. If the verification fails, we will get the verification error. Prepare, for all static variables, memory will be allocated and assigned with default values. Resolved, the all symbolic memory references are replaced with the original references from method area. And initialization, this is the final phase of class loading. Here all static variable will be assigned with the original values and the static block will be executed. Runtime data area. The runtime data area is divided into 5 major components. Method area, all the class level data will be stored here, including static variables. There is only one method area per JVM and it is a shared resource. Heap area, all the objects and their corresponding instance variables and arrays will be stored here. These are also one heap area per there is also one heap area per JVM. Since the method and heap areas share memory for multiple threads, the data stored is not thread safe. Stack area, for every thread, a separate runtime stack will be created. For every method call, one entry will be made in the stack memory, which is called stack frame. All local variables will be created in the stack memory. The stack area is thread safe since it is not shared resource. The stack frame is divided into 3 sub entries. Local variable array, related to the method, how many local variables are involved and the corresponding values will be stored here. Operand stack, if any immediate operation is required to perform, operand stack acts as a runtime workspace to perform the operation. Frame data, all symbols corresponding to the method is stored here. In case of any exception, the catch block information will be maintained in the frame data. PC registers, each thread will have separate PC registers to hold the address of current execution instruction. Once the instruction is executed, the PC register will be updated with the next instruction. Native method stack. Native method stack holds native method information. For every thread, a separate native method stack will be created. Execution engine. The bytecode which is assigned to the runtime data area will be executed by execution engine. The execution engine reads the bytecode and execute it piece by piece. Interpreter. The interpreter interprets the bytecode faster but executes slowly. The disadvantage of the interpreter is that when one method is called multiple times, every time a new interpretation is required. GIT compiler. The GIT compiler neutralizes the disadvantage of the interpreter. The execution engine will be using the help of the interpreter in converting bytecode, but when it finds repeated code, it uses GIT compiler, which compiles the entire bytecode and changes it to a native code. This native code will be used directly for repeated method calls, which improve the performance of the system. Intermediate code generator produces intermediate code. Code optimizer, responsible for optimizing the intermediate code generated above. Target code generator, special responsible for generating machine code for native or native code. Profiler, a special component responsible for finding hotspots, that is whether the method is called multiple times or not. A profile is here. Garbage collector collects and removes unreferenced objects. Garbage collection can be triggered by calling system.gc, but the execution is not guaranteed. Garbage collection of the JVM collects the objects that are created. JNI, Java native interface. JNI will be interacting with the native method libraries and provide native libraries required for execution engine. Native method libraries. This is a collection of native libraries which is required for the execution engine. Here you can see class loader subsystem interact with stack runtime data areas. Runtime data areas interacts with execution engine and native method interface. Class file is connected to class loader subsystem. Loading is connected to linking. Linking is connected to initialization in class loader subsystem. Bootstrap class load is connected to execution class loader. Execution class load is connected to application class loader. Verify is connected to prepare. Prepare is connected to resolve. Method area, heap area, stack area, and PC register and native method stacks are in stack and in runtime data areas. Threads are in stack area. In thread, stack frame, LVA, OS, and PD, FD frame data and are there. PC register for thread 1, PC register for thread 2, and PC register for thread N, and there are in PC registers. Interpreter, GIT compiler, and garbage collections are in execution engine. In GIT compiler, intermediate code generator is connected to code optimizer. Code optimizer is connected to target code generator, and profile also in GIT compiler. and execution engine interacts with native method interface. Native method interface interacts with native method library. As an example, we can consider this standard options for Java VM options: module dash module dash path, module path, or dash p module path, semicolon separated list of directories in which each directory is a directory of modules. Standard options for Java dash add dash modules. Module specifies the root modules to resolve in addition to the initial module. Modules also can be all default, all system, and all module path. Now we are considering run hello world using JavaFX SDK. Finally run the application using this command here, and this is in Linux or Mac, and this is for Windows. Make sure to add the required module creeping into the account. Transitive dependencies automatically solved. For instance, there is no need to add JavaFX.graphics module since it is transitively required by the JavaFX.controls module. Here command Java launches a Java application. An error example, we can consider the error occurred with this JVM options. In this specific case, error could not create the Java virtual machine. Error a fatal exception has occurred. Program will exit. This is end of my presentation. Thank you very much for watching.